Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast stellar nurseries where stars are born from the collapse of ancient gas and dust. If you find peace or curiosity in these gentle stories, please consider liking that video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 7,000 light years from Earth, the Eagle Nebula stretches across space like a cosmic cathedral. Its towering pillars of gas and dust rise through the darkness, each column spanning several light years from base to tip. From our perspective, these monuments to stellar creation appear no larger than grains of rice held at arm's length, yet they dwarf our entire solar system. The famous pillars of creation represent just one small region within this vast stellar nursery, where gravity performs its patient, inexorable work across timescales that render human civilization a brief flicker. Within these pillars, hydrogen atoms drift in near-perfect solitude. The density here measures just a few hundred atoms per cubic centimetre, a vacuum so complete that Earth's best laboratory chambers seem crowded by comparison. To walk through such a region, if walking were possible, would be to experience emptiness beyond terrestrial comprehension, yet this apparent void conceals profound activity, invisible processes that will ultimately give birth to the very furnaces that illuminate our night sky. The temperature in these stellar nurseries hovers near absolute zero, just a few degrees above the point where all atomic motion would cease entirely. Hydrogen molecules move with languid slowness through the cosmic cold, their thermal energy barely sufficient to maintain gaseous form. Dust grains, each no larger than particles of cigarette smoke, provide surfaces where atoms can briefly pause and sometimes combine into more complex molecules. These microscopic encounters occur across volumes so vast that entire civilizations could rise and fall in the time it takes for significant chemical changes to occur. Yet gravity remains patient. For millions of years, perhaps tens of millions, these pillars exist in delicate equilibrium, the outward pressure of gas, heated by distant stars, balances against the inward pull of gravity. Magnetic fields thread through the plasma like invisible cables, sometimes supporting the structure, sometimes destabilizing it. The interplay of these forces creates a cosmic ballet performed in slow motion, each movement requiring millennia to complete. What triggers the final collapse towards stellar birth remains partially mysterious to astronomers. Perhaps a nearby supernova sends shock waves rippling through the nebula at speeds approaching 1,000 kilometers per second. The compression from such a blast wave might be enough to tip the gravitational balance. Maybe the spiral arms of our galaxy, rotating with stately precision every 200 million years, compress the gas as they sweep through this region of space. These spiral density waves act like cosmic traffic jams, slowing material and increasing its local concentration, or possibly. In the deepest quiet of interstellar space, the material simply reaches some critical threshold known only to the mathematics of stellar formation. The precise conditions required remain elusive. Too little mass and gravity never overcomes thermal pressure. Too much turbulence and the cloud disperses before collapse can begin. Scientists observe the aftermath through radio telescopes and infrared cameras, mapping the warm glow of newborn protostars. But they can only theorize about the exact moment when stillness transforms into motion. The process begins so gradually that it defies observation. Over perhaps 50,000 years, a region of space no more massive than our Sun starts to contract. The collapse accelerates as gravity strengthens with increasing density. What began as a cloud spanning light years shrinks to the size of the outer solar system, then to Jupiter's orbit, then to dimensions comparable to our own planetary neighborhood. Temperature rises as gravitational potential energy converts to heat. The contracting gas begins to glow, first in infrared wavelengths invisible to human eyes, then eventually in visible light as nuclear fusion ignites in the deepest core. This transformation from cold gas to burning star requires roughly 10 million years, a duration that encompasses the entire span of human history, repeated 1,000 times over. The irony settles like cosmic dust through the contemplation these stellar nurseries, among the most violent and energetic phenomena in the universe, appear utterly serene through our telescopes. Photographs reveal pillars of ethereal beauty, glowing softly in the red light of ionized hydrogen, their edges sculpted by stellar winds into shapes resembling cosmic sculptures. Only took a few million years for a cloud of hydrogen to decide it wanted to become a star. The casual violence required to forge these celestial furnaces proceeds with such gentleness that we perceive it as beauty rather than destruction. Mountains of gas and dust, each containing enough material to create hundreds of stars like our Sun, simply drift and swirl until gravity finally wins its ancient contest against pressure and turbulence. The pillars themselves exist as temporary monuments to stellar creation. Radiation and stellar winds from newly formed stars gradually erode these structures, like cosmic weather wearing away cosmic mountains. The very stars born within these nurseries will eventually destroy their birthplaces, scattering the remaining gas and dust back into the interstellar medium. Within another million years, the famous pillars of creation will likely be gone, remembered only in the photographs captured by space telescopes during humanity's brief moment of technological awareness. Yet tonight, their light reaches us with perfect punctuality, carrying information encoded in photons that began their journey when our planet was still learning to harbour complex life. Each wavelength tells a story: hydrogen glowing red, oxygen shining green, sulfur appearing blue in false color images. The spectrum reveals not only which elements populate these distant clouds, but also their temperature, density, and motion through space. Each new star represents a portal opening not to another dimension, but to a future stretching across billions of years. The stellar collapse beginning now in some remote corner of the Eagle Nebula will determine whether this newborn sun burns for 10 million years or 100 billion, whether it will end as a white dwarf cooling slowly in the darkness, a neutron star spinning with impossible speed, or a black hole from which not even light can escape. All of this cosmic destiny, written in the initial mass of gas that happens to fall inward on some unremarkable moment in the nebula's long, slow dance with time. The mathematics prove elegant in their simplicity. Stars more massive than 8 times our Sun will explode as supernova, while smaller stars will burn steadily for eons before gently expelling their outer layers as planetary nebulae. Yet predicting which fate awaits any particular collapsing cloud requires measurements precise to within a few %, the difference between stellar immortality and spectacular death, encoded in the gravitational attraction of a few additional solar masses, Deep within the stellar core that emerged from yesterday's collapsing cloud, hydrogen atoms begin their ancient dance of fusion. The temperature here exceeds 15 million degrees Celsius, hot enough to strip electrons from their atomic nuclei and create a plasma so energetic that matter exists in a state unknown anywhere on Earth's surface. Pressure reaches 250 billion times that of our atmosphere, compressing hydrogen nuclei until they overcome their natural electrical repulsion and fuse into helium. This process, called nuclear fusion, represents one of the universe's most fundamental transformations. 4 hydrogen nuclei, each containing a single proton, combine through a series of reactions to create one helium nucleus containing 2 protons and 2 neutrons. The mathematics appear deceptively simple, yet the reality involves quantum mechanics operating at scales where particles exist in multiple states simultaneously and tunnel through energy barriers that classical physics would deem insurmountable. The proton-proton chain reaction begins when 2 hydrogen nuclei collide with sufficient energy to overcome their mutual electromagnetic repulsion. At the temperatures found in stellar cores, nuclei move at speeds approaching 300 kilometers per second. Yet even this tremendous thermal motion provides barely enough energy for fusion to occur. The reaction proceeds only because quantum mechanics allows particles to tunnel through energy barriers, appearing on the other side despite lacking the classical energy required to climb over the barrier. What scientists find particularly elegant about stellar fusion is its self-regulating nature. If the core temperature rises too high, fusion rates increase exponentially, generating more energy and expanding the stellar interior. This expansion cools the core, reducing fusion rates and allowing the star to settle back into equilibrium. If the core cools too much, reduced fusion rates cause the core to contract under gravity, raising temperature and density until fusion increases again. Stars spend most of their lives in this delicate balance, neither exploding from runaway fusion nor collapsing under their own gravity. The helium nuclei created through fusion remain trapped in the stellar core for the star's entire main sequence lifetime. Unlike the hydrogen fuel that flows freely throughout the stellar interior, helium accumulates like ash in a cosmic fireplace. This gradual buildup of helium ash slowly changes the core's composition and density, setting the stage for the dramatic transformations that will mark the star's eventual evolution beyond the main sequence. Each fusion reaction releases 26.7 million electron volts of energy, a number that means little until multiplied by the staggering rate at which these reactions occur. In our Sun alone, approximately 600 million tons of hydrogen fuse into helium every second, converting 4 million tons of matter directly into energy, according to Einstein's famous equation, EN=mc2. This energy generation rate means that every second, the Sun produces more energy than human civilization has consumed throughout its entire history. Yet the energy created in the core faces a journey of epic proportions before reaching the surface. Photons generated by fusion begin their outward migration at the speed of light, but the dense plasma of the stellar interior presents an almost impenetrable obstacle course. Each photon travels only a few centimeters before colliding with an electron or ion, absorbed and re-emitted in a random direction. This process, called radiative diffusion, transforms what should be a straight-line journey of 2.3 seconds into a random walk lasting between 100,000 and 1 million years. The photons that emerge from the Sun's surface today began their journey in the core during the Pleistocene epoch, when early humans were developing stone tools and mammoths roamed the Earth. Some photons now warming your skin started their outward migration before our species learned to control fire. The light reaching us represents not the sun's present state, but rather a delayed message from deep time, encoded in electromagnetic radiation that has spent eons struggling toward the surface. This temporal disconnect creates one of astronomy's most poignant ironies. We observe stars as they appeared years, decades, or centuries ago, never as they exist in the present moment. The star Betelgeuse, visible in winter skies, might have already exploded as a supernova, its death throes racing toward us at light speed but still centuries away from arrival. Only took 8 minutes for sunlight to travel from surface to Earth, but 100,000 years to travel from core to surface. Scientists have discovered that stellar cores operate like natural particle accelerators, creating not only helium from hydrogen, but also trace amounts of heavier elements through side reactions. Lithium, beryllium, and boron form in tiny quantities during the proton-proton chain, though most of these fragile nuclei are quickly destroyed by further collisions. The core also produces neutrinos, ghostly particles that interact so weakly with matter that they stream directly from the fusion region to space without delay, carrying away roughly 2% of the fusion energy. These neutrinos provide astronomers with a real-time window into stellar cores. Unlike photons, which require millennia to reach the surface, neutrinos escape immediately and travel to Earth at nearly light speed. Detectors buried deep underground occasionally capture these stellar neutrinos, allowing scientists to study fusion processes occurring at this very moment in the Sun's core. The neutrino flux reveals that fusion rates match theoretical predictions within a few percent, confirmation that our understanding of stellar physics correctly describes events occurring under conditions impossible to reproduce in terrestrial laboratories. The precision required for sustained stellar fusion reveals another cosmic mystery. If the strong nuclear force were slightly weaker, hydrogen nuclei could never overcome electromagnetic repulsion to fuse. If slightly stronger, all hydrogen would have fused shortly after the Big Bang, leaving no fuel for star formation. The electromagnetic force requires equally fine-tuning too weak, and electrons could not bind to nuclei. Too strong and fusion would never occur. Stars exist only because the fundamental constants of physics fall within narrow ranges that permit both atomic structure and nuclear fusion. Perhaps most remarkably, stellar fusion creates conditions that would be lethal to any form of matter we recognize. Yet this violence generates the gentle warmth that makes life possible on distant planets. The same process that destroys hydrogen nuclei and converts matter to energy ultimately powers photosynthesis in every plant, drives weather patterns across every world, and provides the temperature gradients that allow liquid water to exist on planetary surfaces. Stellar cores serve as cosmic furnaces, transforming the simplest element into slightly more complex ones, while releasing the energy that illuminates and warms the universe. The fusion process will continue in stars like our Sun for approximately 10 billion years, slowly consuming the hydrogen fuel accumulated during stellar formation. Main sequence stars burn with remarkable stability, varying their energy output by less than 1% over millions of years. This steady fusion creates the thermal pressure that prevents gravitational collapse, maintaining stars in hydrostatic equilibrium throughout most of their lives. Only when core hydrogen becomes exhausted will the balance shift, triggering the dramatic evolutionary phases that transform main sequence stars into red giants, white dwarfs, neutron stars, or black holes. The photons created in yesterday's fusion reactions begin the longest journey of their existence, a random walk through the stellar interior that will test the patience of light itself. Each photon emerges from nuclear fusion carrying precisely the energy released when hydrogen nuclei overcome their electromagnetic repulsion and bind together as helium. These high-energy gamma rays possess wavelengths measured in picometers, billions of times shorter than the light visible to human eyes, and energies capable of breaking molecular bonds or ionizing atoms. Yet the stellar interior presents an environment so dense that even light, the universe's ultimate speed limit, becomes trapped in a maze of interactions. The plasma surrounding the fusion core contains roughly 150 grams of matter per cubic centimeter, 10 times denser than lead, and packed with free electrons that scatter photons in every direction. Each collision absorbs the original photon and re-emits it at a slightly different wavelength and in a completely random direction, transforming what should be a straight-line journey into a three-dimensional random walk of staggering complexity. The mathematics of radiative diffusion reveal the true scope of this photonic odyssey. A photon travelling in a straight line would traverse the Sun's radius in 2.3 seconds, but random scattering extends this journey to approximately 100,000 years. Some photons complete their migration in as little as 10,000 years, while others require more than 1 million years to reach the surface. The average photon experiences roughly 10 trillion collisions during its outward journey, each interaction changing its direction and gradually reducing its energy through the process physicists call thermalization. This gradual energy loss transforms high-energy gamma rays into the gentler radiations that ultimately reach planetary surfaces. With each scattering event, photons surrender small amounts of energy to the stellar plasma, heating the material through which they pass. The original gamma-ray photons spawn countless lower-energy photons, ultraviolet, visible light, and infrared radiation, creating a cascade of electromagnetic energy that spreads throughout the stellar interior like ripples from a stone dropped in cosmic waters. Scientists have mapped this photonic migration through computer simulations that track millions of individual photon paths. The calculations reveal a process resembling Brownian motion, where each photon follows a jagged, unpredictable path determined by quantum mechanical interactions. Some photons migrate directly outward, reaching the surface relatively quickly. Others drift sideways or even inward for extended periods, before eventually finding their way to the stellar surface. A few unlucky photons become trapped in circulation patterns that delay their escape for hundreds of thousands of additional years. The stellar interior divides into distinct zones based on how energy propagates outward. In the innermost radiative zone, photon diffusion dominates energy transport. Here, matter remains so dense that convection cannot occur. Hot gas cannot rise because the surrounding plasma maintains nearly identical temperature and density. Energy moves only through the slow diffusion of photons, creating temperature gradients so gradual that thermal equilibrium extends across vast regions of the stellar interior. This radiative transport creates what astronomers call the stellar temperature gradient. Moving outward from the fusion core, temperature drops steadily but slowly, declining from 15 million degrees at the center to roughly 2 million degrees at the radiative zone's outer boundary. Pressure decreases even more dramatically, falling by factors of thousands as the weight of overlying material diminishes with distance from the center. Yet despite these changing conditions, photons continue their random migration, gradually thermalized but never destroyed. The photons that began as high-energy gamma rays in the stellar core eventually emerge as a continuous spectrum of electromagnetic radiation. The Sun's surface temperature of approximately 800 degrees Celsius determines this spectrum's peak wavelength, which falls in the yellow-green portion of visible light. Yet the surface also emits ultraviolet radiation, infrared light, radio waves, and even small amounts of X-rays, all descendants of the gamma-ray photons created through fusion deep in the core. What remains particularly mysterious to stellar physicists is how photons maintain their collective behavior during this extended migration. Despite countless random interactions, the energy flow from core to surface remains remarkably steady. The Sun's luminosity varies by less than 0.1% over timescales of years, suggesting that photon diffusion proceeds with clockwork regularity despite its fundamentally random nature. This stability emerges from the law of large numbers, while individual photons follow chaotic paths. The collective behavior of trillions of photons creates predictable energy transport rates. The temporal implications of photon diffusion create one of astronomy's most profound ironies. We observe stellar surfaces as they exist at the moment light left them, but this light carries information about fusion processes that occurred millennia ago. The energy warming Earth today was created in the Sun's core when the last ice age was ending and human civilization was discovering agriculture. Stellar astronomy thus becomes a form of time travel, allowing us to study ancient nuclear processes through light that has only recently completed its epic migration to the surface. Only took 100,000 years for light to travel the equivalent distance of driving around Earth's equator 25 times. The cosmic speed limit becomes meaningless when matter itself creates obstacles that force even massless particles to take the scenic route. Some photons now reaching Earth began their outward journey before our species developed written language, carrying messages encoded in electromagnetic radiation from an era when woolly rhinoceros still roamed European plains. Modern neutrino astronomy provides a striking contrast to this photonic delay. Neutrinos created alongside photons in fusion reactions interact so weakly with matter that they stream directly from the stellar core to space without scattering. These ghostly particles reach Earth approximately 8 minutes after their creation, providing real-time information about fusion processes currently occurring in stellar cores. Neutrino detectors thus observe the Sun as it exists today, while optical telescopes show us the Sun as it existed during the late Pleistocene epoch. The physics of photon diffusion also explains why stars maintain such stable luminosity over geological timescales. The vast reservoir of photons trapped within stellar interiors acts like a cosmic flywheel, smoothing out short-term variations in fusion rates. Even if fusion stopped completely, stars would continue shining for tens of thousands of years as trapped photons gradually work their way to the surface. This temporal buffering helps maintain stable energy output despite the quantum mechanical fluctuations inherent in nuclear fusion processes. Each photon that finally escapes stellar gravity carries within its wavelength and polarization the history of its lengthy journey. Spectroscopic analysis reveals not only the temperature and composition of stellar surfaces, but also subtle signatures of the physical processes that shaped photons during their migration through stellar interiors. These electromagnetic messengers thus serve as cosmic archaeologists, preserving information about conditions that existed deep within stars thousands of centuries ago. The journey concludes when photons finally reach the stellar surface and escape into the vacuum of space. Here, freed from the dense plasma that has constrained their motion for millennia, they resume traveling at light speed toward whatever destinations await in the cosmic darkness. Some will warm planetary surfaces, some will be absorbed by interstellar dust, and others will travel for billions of years across the expanding universe until they redshift into invisibility. Yet all carry the same fundamental message, the signature of nuclear fusion. Delayed by the patient physics of photon diffusion, finally delivered to the waiting cosmos. Astronomers have spent centuries learning to read the language that stars speak through their light. Each star emits a continuous spectrum of electromagnetic radiation. But this spectrum contains countless dark absorption lines, precise wavelengths, where atoms in the stellar atmosphere have absorbed specific colours of light. These spectral lines serve as stellar fingerprints, revealing not only which elements populate distant suns, but also their temperature, pressure, density, magnetic field strength, and motion through space. The classification system that emerged from this spectroscopic detective work divides stars into 7 primary types, designated by the letters O, B, A, F, G, K, and M. This sequence, memorized by generations of astronomy students through the mnemonic "Oh be a fine girl, cha guy, kiss me," represents a temperature scale running from hottest to coolest. O-type stars burn with surface temperatures exceeding 30,000 degrees Celsius, appearing blue-white and consuming their nuclear fuel at prodigious rates. These stellar giants live fast and die young, exhausting their hydrogen reserves in just a few million years before exploding as supernovae. B-type stars, slightly cooler at 20,000 degrees, still burn blue-white and face similarly brief lifespans measured in tens of millions of years. A-type stars like Sirius shine white-hot at temperatures around 9,000 degrees Celsius, while F-type stars such as Procyon glow yellowish-white at roughly 7,000 degrees. Our Sun belongs to the G-type classification, with its surface temperature of a 5 of 800 degrees producing the yellow light that illuminates our planetary system. K-type stars burn orange at temperatures near 4,500 degrees, and the coolest M-type stars glow red at temperatures below 3,500 degrees Celsius, barely hot enough to maintain hydrogen fusion in their cores. Each spectral class reveals distinct chemical signatures written in absorbed wavelengths. O and B stars show prominent lines from highly ionized helium and hydrogen, elements that require extreme temperatures to strip multiple electrons from their atomic nuclei. The hydrogen-Balmer series dominates A-type stellar spectra, while F and G stars display increasingly complex patterns as metals astronomers term for all elements heavier than helium become more prominent in their atmospheres. K and M stars show molecular absorption bands from compounds like titanium oxide and water vapor, chemicals that can exist in gaseous form only at the relatively cool temperatures found on red dwarf surfaces. The relationship between stellar mass, temperature, and lifetime follows patterns that reveal fundamental truths about stellar physics. More massive stars burn hotter and brighter, consuming their nuclear fuel at rates that scale with roughly the 4th power of their mass. A star 10 times more massive than the Sun burns roughly 10,000 times more brightly, reducing its main sequence lifetime to about 10 million years compared to the Sun's 10 billion year lifespan. This inverse relationship between mass and longevity creates one of the universe's cruelest ironies. The most spectacular stars live the shortest lives. What remains puzzling to stellar astronomers is why stars form with such a specific distribution of masses. The initial mass function, discovered through surveys of star-forming regions, shows that low-mass stars vastly outnumber their more massive cousins. For every O-type giant that forms, hundreds of M-type dwarfs condense from the same molecular clouds. This pattern appears universal across different galaxies and star formation epochs, suggesting that fundamental physics constrains the stellar mass spectrum in ways that theorists still struggle to fully understand. Brown dwarfs, objects too massive to be planets but too small to sustain hydrogen fusion, occupy a special place in this classification scheme. These failed stars shine dimly in infrared wavelengths, powered by gravitational contraction and the brief fusion of deuterium-heavy hydrogen during their youth. Brown dwarfs cool steadily throughout their lives, eventually becoming invisible even to infrared telescopes. They represent the universe's most common stellar mass objects, yet remained completely unknown to astronomy until the 1990s due to their extreme faintness. The discovery of brown dwarfs required new spectral classifications L and T types to describe objects cooler than the reddest M stars. L dwarfs show absorption bands from exotic molecules like chromium hydride and iron hydride, compounds that exist nowhere else in the universe except in these ultra-cool atmospheres. T dwarfs display prominent methane absorption features, creating spectra more resembling those of Jupiter than traditional stars. Some of the coolest brown dwarfs have surface temperatures below 500 degrees Celsius, cooler than Venus, and approaching conditions found on rocky planets in habitable zones. Modern spectroscopy reveals subtle details that escaped earlier astronomers. Magnetic fields on stellar surfaces split spectral lines through the Zeeman effect, allowing measurement of field strengths that often exceed Earth's magnetic field by factors of thousands. Stellar rotation broadens absorption lines as different portions of the stellar surface move toward and away from Earth, enabling astronomers to measure spin rates for stars too distant to resolve as disks. Even gravitational redshift becomes detectable in the spectra of white dwarfs, where intense gravity stretches wavelengths by measurable amounts. Chemical abundances determined through spectroscopic analysis tell stories of stellar nucleosynthesis and galactic chemical evolution. Stars form from gas clouds enriched by previous generations of stellar death, and their atmospheric compositions reflect this chemical heritage. Population-wide stars, like our Sun, contain roughly 2% heavy elements forged in earlier supernovae. Population 2 stars, formed when the galaxy was young, show heavy element abundances reduced by factors of 10 to 1,000, preserving chemical signatures from an era when the universe contained mostly primordial hydrogen and helium. Only took 4 billion years for the galaxy to increase its metallicity from nearly zero to the levels observed in solar-type stars. This chemical enrichment occurred through countless stellar life cycles, massive stars creating elements like oxygen, silicon, and iron through fusion and explosive nucleosynthesis, then distributing these products through supernova explosions. Lower mass stars contributed carbon, nitrogen, and fluorine through stellar winds during their red giant phases. Each generation of stars formed from materials slightly more enriched in heavy elements than its predecessors. The precision of modern stellar classification extends beyond simple temperature measurements. Astronomers now recognize luminosity classes that distinguish between main sequence stars, giants, and supergiants of the same spectral type. These classifications reveal stellar evolutionary states, main sequence stars burning hydrogen in their cores, giants fusing helium in their centers while burning hydrogen in surrounding shells, and supergiants undergoing the complex nuclear processes that mark the final phases of stellar evolution. Peculiar stars defy standard classification schemes, showing chemical abundances or spectral features that suggest unusual evolutionary histories. Chemically peculiar A stars display enhanced abundances of rare Earth elements like europium and gadolinium, possibly due to radiative diffusion in their stable atmospheres. Carbon stars show carbon-to-oxygen ratios greater than unity, indicating that convective dredge-up has brought carbon-rich material from their cores to their surfaces. Wolf-Rayet stars display emission lines from highly ionized nitrogen, carbon, and oxygen, revealing cores exposed by stellar winds so powerful they strip away entire stellar envelopes. Variable stars add temporal dimensions to spectral classification. Cepheid variables pulsate with periods ranging from days to months, their spectra cycling between earlier and later types as their surfaces expand and contract. RR-Lyrae stars show similar behavior on shorter timescales, while long-period variables like Mira stars undergo dramatic spectral changes as their extended atmospheres cool and warm over cycles lasting hundreds of days. These pulsating stars serve as cosmic laboratories where astronomers study stellar atmospheres under extreme and rapidly changing conditions. Each star observed through modern telescopes represents a unique combination of mass, age, composition, and evolutionary state. Yet all stellar spectra follow patterns established by fundamental physics, the same quantum mechanical transitions that governed laboratory spectra on Earth also determine which wavelength stars absorb and emit. This universality allows astronomers to study stellar physics across vast distances, learning about nuclear fusion, atmospheric dynamics, and chemical evolution in environments impossible to recreate in terrestrial laboratories. The classification of stellar spectra thus becomes a form of cosmic archaeology, revealing the physical conditions and chemical compositions of suns scattered throughout the galaxy and beyond. When stars exhaust the hydrogen fuel in their cores, they begin a transformation that will define the final chapters of their cosmic existence. The delicate balance between gravitational collapse and thermal pressure, maintained for billions of years through steady hydrogen fusion, shifts irrevocably as helium ash accumulates in the stellar center. This helium core, initially about the size of Earth, but containing roughly 10% of the star's total mass, cannot yet achieve the temperatures required for helium fusion. Without nuclear energy to support it against gravity, the core begins to contract while the surrounding hydrogen-rich envelope responds by expanding outward into the cold vacuum of space. This expansion occurs with geological patience, unfolding over millions of years as the star's outer layers cool and swell. A star like our Sun will eventually grow to encompass the orbit of Mars, its surface temperature dropping from 5,800 degrees to perhaps 3,500 degrees Celsius. The luminosity increases dramatically, sometimes by factors of hundreds or thousands, as the vastly expanded surface area more than compensates for the reduced temperature. These swollen giants glow with ruddy light, their extended atmospheres so tenuous that they barely qualify as matter by terrestrial standards. The physics governing red giant evolution reveals the elegant interconnection between stellar structure and nuclear processes. As the helium core contracts under its own gravity, gravitational potential energy converts to heat, raising the core temperature even though no fusion occurs within it. This heating affects the hydrogen-burning shell surrounding the core, where increased temperature accelerates fusion rates exponentially. The shell burns hydrogen more vigorously than the star's core ever did during its main sequenced lifetime, generating energy at rates that force the outer envelope to expand until radiative cooling from the enlarged surface balances the enhanced nuclear energy production. What makes red giant evolution particularly fascinating is the development of convective zones throughout the stellar interior. The outer envelope becomes convective as its low temperature and density create conditions where hot gas rises and cool gas sinks in vast circulation patterns. These convection cells transport material from deep within the star to its surface, dredging up products of nuclear processing that were previously hidden in the stellar interior. Elements like carbon and nitrogen, created through hydrogen burning via the CNO cycle, appear for the first time in the stellar atmosphere during this first dredge-up event. The helium core continues contracting until electron degeneracy pressure a quantum mechanical effect arising from the Pauli exclusion principle finally halts further compression. In this exotic state of matter, electrons pack so tightly that quantum mechanics forbids additional compression, regardless of the gravitational forces involved. The core reaches densities exceeding 1 million grams per cubic centimetre, where a sugar cube would weigh as much as an automobile. Yet this degenerate matter supports the core through pressure that depends on density rather than temperature, creating conditions unlike anything found elsewhere in the universe. Temperature in the contracting core eventually reaches 100 million degrees Celsius, hot enough to ignite helium fusion through the triple alpha process. 3 helium nuclei must collide nearly simultaneously to create carbon, since the intermediate beryllium-8 nucleus exists for only 10 radians to 16 seconds before decaying. This reaction requires precise coordination temperatures too low, and the reaction rate becomes negligible. Temperatures too high, and the newly formed carbon immediately fuses with additional helium to create oxygen. The narrow temperature window for stable helium burning creates another example of the fine-tuning that characterizes stellar nuclear synthesis. The onset of helium fusion in degenerate matter triggers what astronomers call the helium flash, a runaway nuclear explosion that occurs deep within the red giant's interior. Because degenerate matter's pressure depends on density rather than temperature, the initial burst of helium fusion cannot expand and cool the core as normal gas would. Instead, rising temperature accelerates fusion rates exponentially, releasing energy equivalent to the entire luminosity of our galaxy for a few seconds. Fortunately for any nearby planetary systems, this explosion occurs so deep within the star that its effects remain hidden beneath millions of solar masses of overlying material. The helium flash fundamentally restructures the stellar interior, converting the degenerate core back to normal gas and establishing a new phase of stable helium burning. The star settles into a configuration with helium fusing to carbon and oxygen in the core, while hydrogen continues burning in a surrounding shell. This double shell burning phase creates complex interactions between the two fusion zones, leading to thermal pulses that periodically disrupt the stellar structure and drive additional dredge-up events that bring freshly synthesized elements to the surface. Scientists find red giant evolution particularly important for understanding galactic chemical evolution. These stars produce significant quantities of carbon, nitrogen, and fluorine through nuclear processing, then distribute these elements throughout the interstellar medium via stellar winds. Mass loss rates during the red giant phase can reach 10⁻⁶ solar masses per year, roughly the mass of Earth expelled annually into space. Over the typical red giant lifetime of 1 million years, stars can lose 20 to 30% of their initial mass, enriching the surrounding medium with processed material that will eventually form new generations of stars and planets. The extended atmospheres of red giant stars create conditions where unusual chemistry can occur. Temperatures drop sufficiently to allow the formation of molecules like water vapor, carbon monoxide, and even simple dust grains composed of silicates or carbon compounds. These dust particles absorb starlight and re-emit it in infrared wavelengths, making red giants among the brightest infrared sources in the sky. The dust formation process remains incompletely understood, but appears to involve complex interactions between stellar pulsations, shock waves, and the condensation of refractory materials in the cooling stellar wind. Variable star behavior becomes common during red giant evolution, as the extended stellar envelope becomes unstable against pulsations. Many red giants undergo semi-regular or irregular brightness variations as their surfaces expand and contract in response to changing internal conditions. The most extreme cases become long-period variables like mirror stars, which can vary in brightness by factors of hundreds over periods lasting months to years. These pulsations help drive mass loss by levitating material in the outer atmosphere until stellar radiation pressure and magnetic fields can accelerate it to escape velocity. Only took 10 billion years of steady hydrogen burning for the Sun to reach this evolutionary crossroads, but the red giant phase will unfold in just a few million years, a cosmic eye blink compared to main sequence longevity. The irony of stellar evolution becomes apparent in this disparity. Stars spend the vast majority of their lives burning hydrogen with remarkable stability, then undergo dramatic transformations during the final few percent of their existence. Red giant evolution represents stellar middle age rather than true senescence, yet it marks the beginning of the end for stars like our Sun. The red giant phase concludes when the star has lost sufficient mass that thermal pulses can no longer be sustained. The remaining helium-burning core, now surrounded by a much thinner hydrogen envelope, prepares for the final act of stellar evolution. Depending on the initial stellar mass, this conclusion may involve the gentle expulsion of planetary nebulae and the formation of white dwarf stars, or the more dramatic collapse to neutron stars and black holes. But for now, in the quiet expansion of red giant envelopes, stars experience a cosmic pause, a slow, glowing meditation on the physics of nuclear burning and gravitational balance that has sustained them through billions of years of steady illumination. When the final thermal pulses exhaust a red giant's capacity for nuclear burning, the star enters its terminal phase with remarkable gentleness. The outer envelope, loosely bound by gravity and heated by radiation from the exposed core, drifts away into space over thousands of years. What remains behind defies easy comprehension: a stellar core compressed to the size of Earth, yet containing roughly half the mass of our Sun. This remnant, called a white dwarf, represents matter in a state so exotic that it challenged the fundamental understanding of physics when first discovered in the early 20th century. The physics governing white dwarf structure relies entirely on electron degeneracy pressure, the same quantum mechanical phenomenon that briefly supported red giant cores before helium ignition. Electrons in white dwarf matter pack so tightly that the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state, becomes the primary force resisting gravitational collapse. Unlike normal gas pressure, which depends on temperature, degenerate electron pressure depends only on density, creating a stellar remnant that can support itself indefinitely without nuclear fuel or thermal energy. A typical white dwarf contains approximately 600,000 Earth masses compressed into a volume smaller than our planet. This yields average densities near 1 million grams per cubic centimetre, where a teaspoon of white dwarf material would weigh roughly 6 tons. The surface gravity exceeds Earth's by factors of hundreds of thousands, creating gravitational fields so intense that a marshmallow dropped from 1 metre height would impact the surface with the kinetic energy of a bomb. Yet this extreme environment remains stable across timescales that dwarf the current age of the universe. The composition of white dwarf interiors reflects the nuclear processing that occurred during their progenitor stars' final evolutionary phases. Most white dwarfs consist primarily of carbon and oxygen, the products of helium burning during the asymptotic giant branch phase, more massive progenitors, which achieved higher core temperatures before stellar wind mass loss terminated their evolution, may contain significant amounts of neon and magnesium from carbon burning. The heaviest white dwarfs, approaching the theoretical mass limit, might harbour traces of silicon and sulfur from even more advanced fusion processes. These stellar remnants begin their existence at temperatures exceeding 100,000 degrees Celsius, heated by the gravitational energy released during their final contraction. Yet white dwarfs possess no internal energy source to maintain these temperatures. They cool by radiating thermal energy into space, following a predictable cooling sequence that transforms them from brilliant blue-white objects hotter than any main sequence star to dim red embers barely visible against the cosmic background. This cooling process unfolds with geological patience, requiring billions of years for white dwarfs to fade significantly. The cooling sequence reveals fascinating details about the physics of matter under extreme conditions. Initially, white dwarfs cool rapidly as their surface temperatures drop from 100,000 degrees to roughly 20,000 degrees Celsius. The cooling rate then slows dramatically as the surface temperature approaches 10,000 degrees, marking the transition from radiating primarily in ultraviolet wavelengths to visible light. Further cooling proceeds even more slowly, with white dwarfs requiring tens of billions of years to cool below 5,000 degrees longer than the current age of the universe. What makes white dwarf cooling particularly interesting to astrophysicists is the role of crystallization in their deep interiors. As temperatures drop below approximately 10 million degrees Celsius, the carbon and oxygen nuclei in the white dwarf core begin to arrange themselves into crystal lattices despite the presence of degenerate electrons. This solid-state transition releases latent heat, similar to water freezing into ice, significantly slowing the cooling rate. The crystallization process begins at the center and gradually propagates outward, creating white dwarfs with crystalline cores surrounded by fluid exteriors. The discovery of white dwarf crystallization confirmed theoretical predictions made decades before observational verification became possible. Seismological studies of white dwarf pulsations similar to the techniques used to probe Earth's interior structure revealed the acoustic signatures of partially crystallized interiors. These stellar seismology measurements provide direct evidence for exotic physics occurring under conditions impossible to reproduce in terrestrial laboratories, making white dwarfs natural laboratories for studying matter under extreme pressure and density. Magnetic fields on white dwarf surfaces can reach strengths millions of times stronger than Earth's magnetic field. These intense fields, concentrated by the stellar collapse that created the white dwarf, significantly affect the stellar atmosphere and cooling rate. Magnetic white dwarfs show complex spectral features as their fields split atomic energy levels and channel material along magnetic field lines. The strongest magnetic fields create atmospheres so structured that different regions show dramatically different temperatures and compositions, producing white dwarfs that appear to change their spectral properties as they rotate. Binary white dwarf systems create some of astronomy's most precise gravitational wave sources. Two white dwarfs orbiting each other with periods measured in minutes gradually spiral inward as they radiate energy through gravitational waves ripples in spacetime predicted by Einstein's general relativity. The orbital decay proceeds with clockwork precision, allowing astronomers to test gravitational wave theory to extraordinary accuracy. Some of these systems will eventually merge, possibly triggering Type Ia supernovae that serve as crucial distance indicators for measuring cosmic expansion. The atmospheres of white dwarfs reveal the chemical signatures of their formation process and subsequent evolution. Newly formed white dwarfs show hydrogen and helium in their spectra, remnants of the original stellar envelope that briefly survived the planetary nebula ejection. Over time, gravitational settling causes heavier elements to sink toward the interior while lighter elements float to the surface, creating white dwarfs with nearly pure hydrogen or helium atmospheres. The timescale for this differentiation depends on the white dwarf's mass and temperature, providing clues about the stellar remnant's age and formation history. Some white dwarfs undergo dramatic evolutionary reversals when they accrete material from nearby stellar companions. Matter stolen from red giant companions accumulates on the white dwarf surface until density and temperature become sufficient to trigger explosive hydrogen burning. These nova explosions blast the accumulated material back into space at speeds reaching thousands of kilometers per second, yet leave the underlying white dwarf essentially unchanged. The process can repeat cyclically, creating recurrent novae that explode every few decades as they accumulate fresh material from their stellar companions. Only took a few thousand years for the planetary nebula phase to strip away the red giant envelope, but white dwarf cooling will continue for trillions of years longer than the universe has existed, and far longer than it will remain in its current form. The irony of white dwarf evolution lies in this temporal reversal. Stellar death creates objects more long-lived than the stars that formed them. These stellar corpses will persist long after galaxy mergers have disrupted stellar populations, after the expansion of space has separated galaxy clusters beyond gravitational influence, and after proton decay has eliminated normal matter from the universe. The study of white dwarfs provides crucial insights into stellar evolution, stellar populations, and the future of the cosmos. White dwarf cooling ages allow astronomers to determine the age of the galactic disk by studying the coolest white dwarfs in the solar neighborhood. The white dwarf mass distribution reveals information about the initial mass function of stars formed billions of years ago, and the ultimate fate of white dwarfs cooling to become cold. Dark objects floating through an increasingly empty universe offers a glimpse of cosmic evolution on timescales that dwarf human comprehension. These stellar remnants represent the final resting state for the vast majority of stars, including our Sun. In roughly 5 billion years, our solar system's central star will follow this evolutionary path, swelling into a red giant before gently expelling its outer layers and contracting into a white dwarf roughly the size of Earth. This white dwarf sun will shine dimly for trillions of years, a cosmic monument to 10 billion years of steady hydrogen burning, slowly cooling in the darkness until the last of its thermal energy radiates away into the expanding void of deep space. When stars more massive than 25 times our Sun exhaust their nuclear fuel, they face a gravitational collapse so violent that not even electron degeneracy pressure can halt their contraction. In less than a second, a stellar core larger than Earth compresses to a sphere merely 20 kilometers across, creating an object so dense that atomic nuclei themselves break apart under the crushing gravitational forces. What emerges from this catastrophic implosion defies ordinary physical intuition. A neutron star, where matter exists in a state found nowhere else in the observable universe. The formation process begins when silicon burning in the stellar core produces iron-56, the most stable atomic nucleus. Unlike lighter elements, iron cannot release energy through fusion or fission, making it the ultimate nuclear ash. When the iron core reaches approximately 1.4 solar masses, the Chandrasekhar limit electron degeneracy pressure becomes insufficient to support the stellar remnant against its own gravity. The core collapse accelerates beyond the speed of sound, compressing matter to nuclear density in a gravitational freefall that lasts mere milliseconds. At densities approaching 10^15 grams per cubic centimeter, the electromagnetic forces that maintain atomic structure surrender to gravitational pressure. Electrons and protons merge through inverse beta decay, transforming into neutrons and neutrinos in a process that converts an entire stellar core into essentially a single atomic nucleus. The neutrons pack together as tightly as matter can be compressed before strong nuclear forces create a repulsive pressure sufficient to halt further collapse. The result resembles a city-sized atomic nucleus containing 1.4 times the mass of our Sun. The physics governing neutron star structure operates at the boundary between nuclear physics and general relativity. Matter in the neutron star interior exists at densities several times that found in atomic nuclei, creating conditions where the strong nuclear force dominates over electromagnetic interactions. Theoretical models suggest that neutron star cores might contain exotic forms of matter, quark-gluon plasmas, kaon condensates, or even more speculative states like strange quark matter, though direct observational evidence for these phases remains elusive. Neutron stars rotate with periods ranging from milliseconds to seconds, spinning at rates that would tear apart any normal stellar object. Conservation of angular momentum during the core collapse process concentrates the original star's rotation into an object millions of times smaller, accelerating the spin rate by factors approaching 10 or 10. The fastest known pulsar, PSR J1748 SUS 244468, completes 716 rotations per second fast enough that its equatorial surface moves at roughly 25% of light speed while remaining gravitationally bound to the neutron star. The magnetic fields surrounding neutron stars achieve strength that dwarf terrestrial magnetic phenomena by factors exceeding 10 per 12. These fields, compressed and amplified during stellar collapse, create magnetospheres so intense that they fundamentally alter the behavior of matter and radiation in their vicinity. Charged particles accelerated along magnetic field lines emit synchrotron radiation across the electromagnetic spectrum, from radio waves to gamma rays, creating the lighthouse-like beams that allow astronomers to detect neutron stars as pulsars. Pulsar timing provides some of astronomy's most precise measurements, with the best-studied pulsars maintaining rotational stability comparable to atomic clocks. The Crab pulsar, formed in the supernova observed by Chinese astronomers in 1054 CE, pulses every 33 milliseconds with timing precision that varies by less than a few nanoseconds over periods of years. This remarkable stability allows astronomers to detect minute changes in pulse arrival times caused by gravitational waves, planetary motion, and even the wobble induced by unseen planetary companions. What makes neutron star physics particularly fascinating is the relationship between rotation rate and magnetic field strength. Newly formed neutron stars typically possess the strongest magnetic fields and rotate most rapidly, gradually slowing as magnetic dipole radiation carries away rotational energy. Over millions of years, pulsars evolve from millisecond periods to rotation rates measured in seconds, while the magnetic fields decay through complex plasma physics processes that remain incompletely understood. The surfaces of neutron stars present environments more extreme than the interiors of massive stars. Surface temperatures can exceed 1 million degrees Celsius for young neutron stars, though they cool rapidly by neutrino emission during their first few thousand years. Surface gravity approaches 2x 10^11 times Earth's gravity, creating gravitational redshift effects that measurably lengthen the wavelengths of emitted radiation. The intense gravitational field also bends light rays, allowing observers to see more than half of the neutron star's surface simultaneously, despite viewing it from a single direction. Neutron star atmospheres, where they exist, consist of the lightest elements that can remain gravitationally bound under such extreme conditions. Hydrogen and helium form thin atmospheric layers only centimeters thick, yet these tenuous envelopes significantly affect the neutron star's thermal emission and spectral appearance. The atmosphere's composition depends on the neutron star's formation history and subsequent accretion of interstellar material, with some neutron stars showing evidence for heavier elements dredged up from their interiors through magnetic field interactions. Binary neutron star systems provide natural laboratories for testing general relativity under the strongest gravitational fields found in nature. The Hulse-Taylor pulsar, PSR B1913/16, consists of two neutron stars orbiting each other every 7.75 hours, with orbital velocities reaching 300 kilometers per second. Precise timing measurements reveal that the orbital period decreases by 76 microseconds annually, exactly the rate predicted by general relativity for energy loss through gravitational wave radiation. The collision of two neutron stars creates kilonovae, electromagnetic transients powered by the radioactive decay of rapidly synthesized heavy elements. These mergers produce conditions hot and dense enough to create elements heavier than iron through rapid neutron capture processes, forging gold, platinum, and rare earth elements in quantities sufficient to explain their cosmic abundances. The neutron-rich material ejected during these collisions glows for weeks in optical and infrared wavelengths as newly formed radioactive isotopes undergo decay. Only took 30 years from the theoretical prediction of neutron stars in 1934 to their observational discovery as pulsars in 1967, yet many aspects of neutron star physics remain mysterious. The equation of state describing matter at nuclear densities remains uncertain, with different theoretical models predicting neutron star radii varying by several kilometers. The maximum mass that neutron stars can support before collapsing to black holes ranges from 2 to 2.5 solar masses, depending on the poorly understood properties of matter under extreme conditions. Recent gravitational wave detections by LIGO and Virgo have revolutionized neutron star astronomy by providing direct measurements of neutron star masses and tidal deformability during binary mergers. These observations constrain the neutron star equation of state more precisely than decades of electromagnetic observations, revealing that neutron star matter behaves more like a fluid than a solid under tidal stresses. The gravitational wave data also confirms that neutron star mergers produce short gamma-ray bursts and synthesize heavy elements through R-process nucleosynthesis. Neutron stars challenge our understanding of matter, gravity, and magnetism under the most extreme conditions found in the contemporary universe. They serve as cosmic laboratories where the fundamental forces of nature operate in regimes impossible to reproduce in terrestrial experiments. Each pulsar detection adds to a growing census of these exotic objects, revealing the diversity of outcomes possible when stellar evolution reaches its ultimate gravitational limit. These spinning magnetic lighthouses will continue broadcasting their precise signals across the galaxy for millions of years, cosmic metronomes marking time in a universe where even the strongest matter must eventually surrender to the patient persistence of gravity. Beyond the neutron star mass limit lies a boundary that physics cannot cross, a gravitational field so intense that spacetime itself becomes a trap from which nothing, not even light, can escape. When stellar cores exceed approximately 3 solar masses, no known force in the universe can halt their gravitational collapse. The matter disappears behind an event horizon, creating a region where the normal rules of physics break down and time itself slows to a stop as observed from the outside universe. These objects, called black holes, represent the ultimate victory of gravity over all other forces in nature. The formation of stellar mass black holes begins with the same core collapse that creates neutron stars, but proceeds beyond the point where neutron degeneracy pressure can provide support. When the collapsing core exceeds the Tolman-Oppenheimer-Volkoff limit, roughly 2.2 solar masses for realistic equations of state, no force in the standard model of physics can halt the contraction. The matter density approaches infinity at a mathematical singularity, while space-time curvature becomes so extreme that it pinches off from the rest of the universe, creating a black hole surrounded by an event horizon. The event horizon represents a point of no return defined not by a physical surface, but by the geometry of curved space-time. For a black hole of stellar mass, this boundary typically lies just a few kilometers from the central singularity, smaller than most cities yet containing several times the mass of our Sun. Nothing that crosses the event horizon can ever communicate with the outside universe, making black holes the ultimate information paradox. Matter, energy, and even information appear to vanish completely from the observable cosmos, leaving behind only gravitational effects and three measurable properties: mass, electric charge, and angular momentum. The warping of space-time near black holes creates gravitational effects that challenge human intuition about the nature of time and space. Time dilation becomes extreme in the vicinity of the event horizon, where clocks tick increasingly slowly as measured by distant observers. An astronaut falling toward a black hole would experience time normally from their own perspective, but external observers would see them slow down dramatically as they approach the horizon, their image red-shifting toward longer wavelengths until it fades beyond detection. This temporal distortion means that black holes appear frozen in time from the outside, even as matter continuously falls past their event horizons. Gravitational lensing around black holes bends light rays into complex trajectories that can create multiple images of background objects or focus distant starlight into brilliant Einstein rings. The black hole's gravity acts like a cosmic magnifying glass, allowing astronomers to study phenomena that would otherwise remain invisible. This gravitational focusing can amplify the apparent brightness of background stars by factors of thousands during microlensing events, providing one method for detecting isolated black holes that emit no light of their own. The rotation of black holes adds another layer of complexity to their space-time geometry. Spinning black holes drag the surrounding spacetime into motion through frame-dragging effects predicted by general relativity. This rotation creates an ergosphere, a region outside the event horizon, where spacetime itself rotates faster than light, making it impossible for anything to remain stationary relative to distant observers. The Kerr metric, which describes rotating black holes, shows that rapid rotation can significantly increase the size of the ergosphere while decreasing the area of the event horizon. What makes black hole physics particularly mysterious is the information paradox that arises from combining general relativity with quantum mechanics. Classical black holes appear to destroy information completely, violating a fundamental principle of quantum mechanics that requires information to be conserved during physical processes. Stephen Hawking's discovery that black holes emit thermal radiation through quantum effects near the event horizon suggests that black holes eventually evaporate. But this Hawking radiation appears to carry no information about the matter that formed the black hole. The temperature of Hawking radiation depends inversely on the black hole's mass, meaning that stellar mass black holes emit radiation at temperatures near 10^08 Kelvin, billions of times colder than the cosmic microwave background. These black holes actually grow by absorbing background radiation faster than they emit Hawking radiation, and will continue growing until the universe cools sufficiently for evaporation to dominate. For stellar mass black holes, this transition occurs only after the universe has expanded and cooled for 10^67 years, followed by an evaporation timescale of 10^67 years. Binary black hole systems create the strongest gravitational wave sources in the universe as they spiral toward merger. During the final fraction of a second before collision, two stellar mass black holes can radiate more energy and gravitational waves than all the stars in the observable universe emit in electromagnetic radiation. The LIGO and Virgo detectors have recorded dozens of these merger events, revealing a population of stellar mass black holes more massive and more numerous than previously expected. The merger of two black holes produces a single, larger black hole that oscillates like a struck bell before settling into its final configuration. These oscillations, called quasi-normal modes, depend only on the final black hole's mass and spin, allowing astronomers to test general relativity's predictions about black hole properties. The gravitational waves also carry information about the masses and spins of the merging black holes, providing insights into stellar evolution pathways that produce black hole binaries. Supermassive black holes, containing millions to billions of solar masses, lurk at the centers of most galaxies, including our own Milky Way. Sagittarius A, the supermassive black hole at our galactic center, has been directly imaged by the Event Horizon Telescope, revealing the shadow cast by its event horizon against the glowing background of surrounding plasma. These observations confirm theoretical predictions about black hole appearance and provide new tests of general relativity in the strong field regime. The accretion of matter onto black holes can produce some of the most energetic phenomena in the universe. As material spirals inward through an accretion disk, friction and magnetic forces heat the gas to temperatures exceeding 1 billion degrees, causing it to emit X-rays and gamma rays before disappearing behind the event horizon. Jets of relativistic particles, accelerated by magnetic fields threading the ergosphere, can extend for millions of light-years beyond the black hole, creating the radio lobes observed around active galactic nuclei. Only took 50 years from Einstein's theoretical prediction of black holes in his field equations to their first indirect detection through X-ray astronomy. Yet direct observation of event horizons became possible only with the development of very long baseline interferometry techniques in the 21st century. The mathematical description of black holes emerged from pure theory, with solutions to Einstein's equations predicting their existence decades before astronomical observations could confirm their reality. Black holes represent the ultimate endpoints of stellar evolution for the most massive stars. Yet they also challenge our understanding of the fundamental nature of space, time, and information. They serve as natural laboratories for testing general relativity under the most extreme conditions possible, where gravitational fields approach the theoretical maximum strength allowed by Einstein's equations. The study of black holes bridges the gap between astronomy and fundamental physics, revealing connections between gravity, thermodynamics, and quantum mechanics that continue to puzzle theorists. These gravitational monsters will persist long after all stars have exhausted their nuclear fuel and the universe has cooled to near absolute zero. Through Hawking evaporation, they will slowly return their mass energy to the vacuum, taking longer to disappear than the current age of the universe multiplied by countless orders of magnitude. In the far future, when protons have decayed and only black holes remain, their eventual evaporation will represent the universe's final source of free energy, marking the transition to a state of maximum entropy from which no further evolution can occur. Throughout their lives, stars breathe elements into the cosmos with the patience of geological processes and the persistence of stellar winds. These outflows begin as gentle exhalations during the main sequence phase, when stellar radiation pressure drives small amounts of material from stellar atmospheres into the surrounding interstellar medium. The mass loss rates remain modest for most of stellar evolution. Our Sun currently loses approximately 1 billion kilograms per second through the solar wind, a rate so small that it would take trillions of years to affect the star's total mass significantly. Yet this seemingly negligible leakage carries profound consequences for the chemical evolution of galaxies. These stellar winds accelerate charged particles to speeds ranging from hundreds to thousands of kilometers per second through processes that remain incompletely understood. Magnetic fields threading stellar atmospheres may act like cosmic slingshots, flinging material outward through magnetic reconnection events. Radiation pressure from stellar photons can drive mass loss in luminous stars, while acoustic waves generated by convection in stellar interiors might deposit energy in stellar coronae, heating gas to temperatures exceeding 1 million degrees and allowing it to escape gravitational confinement. As stars evolve beyond the main sequence into red giants, their mass loss rates increase dramatically. The extended, tenuous atmospheres of evolved stars become only loosely bound by gravity, making them vulnerable to stellar winds that can carry away significant fractions of the original stellar mass. Asymptotic giant branch stars lose material at rates reaching 10^4 solar masses per year, 10,000 times faster than main sequence stars, creating circumstellar envelopes of gas and dust that can extend for light years around the central star. The composition of stellar winds reveals the nuclear archaeology of stellar interiors. Main sequence stars primarily expel hydrogen and helium, the light elements that dominate stellar atmospheres. But as convective dredge-up brings processed material from stellar cores to their surfaces, evolved stars begin to enrich their winds with heavier elements forged through nuclear fusion. Carbon stars, which have experienced multiple thermal pulses that dredge carbon from their cores, create winds rich in carbon compounds that condense into microscopic dust grains in the cooling circumstellar environment. These dust grains play crucial roles in cosmic chemical evolution despite their microscopic size. Silicate dust forms around oxygen-rich stars, incorporating elements like magnesium, silicon, and iron into crystalline structures similar to terrestrial minerals. Carbon dust condenses around carbon-rich stars, creating graphite and amorphous carbon particles that absorb starlight efficiently and re-radiate it in infrared wavelengths. Both types of dust grains serve as condensation nuclei for additional material, growing through accretion processes until stellar radiation pressure accelerates them to escape velocity. The physics of dust formation in stellar winds operates at the intersection of thermodynamics, nuclear physics, and fluid dynamics. As stellar material expands and cools in the circumstellar environment, temperatures drop below the condensation points of refractory compounds, those materials that remain solid at high temperatures. Aluminum oxide typically condenses first, followed by silicates, then more volatile compounds like water ice and carbon monoxide in the coldest regions far from the star. This condensation sequence mirrors the process that occurred in the early solar system, where temperature gradients determined which materials could form solid particles at different distances from the young sun. Stellar winds carry not only the products of nuclear fusion, but also trace elements synthesized through neutron capture processes. The slow neutron capture process, or S process, occurs in the helium-burning zones of evolved stars, where free neutrons produced by reactions like carbon-13 plus helium-4 can be captured by existing atomic nuclei. This process builds elements heavier than iron through a series of neutron captures and beta decays, creating roughly half of all elements more massive than iron found in the universe today. These process elements synthesized in stellar interiors include strontium, barium, lead, and many of the rare Earth elements essential for modern technology. These elements would remain locked in stellar cores without the convective dredge-up events that transport them to stellar surfaces, where stellar winds can carry them into the interstellar medium. The abundances of S-process elements in stellar winds depend on the neutron flux in stellar cores, the efficiency of convective mixing, and the mass loss rates during the asymptotic giant branch phase. Wolf-Rayet stars represent an extreme example of stellar wind mass loss, expelling material at rates exceeding 10^5 solar masses per year, with velocities reaching several thousand kilometers per second. These evolved massive stars have lost their hydrogen envelopes entirely, exposing cores enriched in helium, carbon, nitrogen, and oxygen through nuclear processing. Their powerful winds carry these processed elements directly into the interstellar medium, enriching nearby gas clouds with the products of advanced nuclear burning phases. The interaction between stellar winds and the interstellar medium creates complex shock structures and cavities carved out of the ambient gas. Main sequence O and B stars create stellar wind bubbles tens of light-year across, where the fast stellar wind collides with slower-moving interstellar material. These collisions generate shock waves that heat gas to millions of degrees and accelerate particles to cosmic ray energies. The shocked gas glows in X-ray wavelengths, creating extended halos around massive stars that reveal the ongoing interaction between stellar outflows and their environments. Binary star systems can dramatically modify stellar wind patterns through gravitational and magnetic interactions between the two stellar components. Wind-wind collisions create shock fronts where the stellar winds from both stars meet, generating high-energy radiation and complex hydrodynamic structures. Some binary systems undergo mass transfer, where material from one star's wind is captured by its companion, leading to phenomena like novae, X-ray binaries, and the formation of exotic stellar remnants with compositions determined by the accreted wind material. The metallicity of stellar winds, their abundance of elements heavier than helium, increases over cosmic time as successive generations of stars synthesize and distribute heavy elements. Population of stars formed in the current epoch show wind compositions enriched in metals by factors of 10 to 100 compared to population 2. Stars formed when the galaxy was young. This chemical evolution creates a feedback loop where metal-rich environments favor the formation of dust-rich stellar winds, which in turn provide the raw materials for planet formation around subsequent generations of stars. Only took 8 billion years for stellar winds to increase the heavy element content of galactic gas from nearly zero to the levels observed in our solar system today. This gradual enrichment occurred through countless stellar life cycles, each contributing processed material to the growing reservoir of metals available for star and planet formation. The oxygen we breathe, the carbon in our bodies, and the iron in our blood all spent eons cycling through stellar interiors before stellar winds delivered them to the molecular clouds from which our solar system eventually formed. Observations of stellar winds provide astronomers with real-time glimpses of stellar nucleosynthesis in action. Spectroscopic studies of wind-blown nebulae around evolved stars reveal the isotopic ratios of freshly synthesized elements, testing theoretical models of nuclear processes occurring in stellar cores. The spatial distribution of different elements in circumstellar envelopes traces the history of nuclear burning phases and convective mixing events, preserving archaeological records of stellar evolution in the patterns of expelled material. Modern space telescopes have revolutionized the study of stellar winds by observing their thermal emission in infrared wavelengths, where dust grains radiate most efficiently. These observations reveal the complex structures created by time-variable mass loss, stellar rotation, and magnetic fields, showing that stellar winds are far from spherically symmetric. Spiral patterns, jets, and clumpy structures in circumstellar envelopes record the detailed history of stellar mass loss over thousands of years. The ultimate fate of material expelled in stellar winds depends on the local galactic environment and the subsequent star formation history of the region. Some wind material remains in the interstellar medium for millions of years before being incorporated into new stellar systems. Other material may be swept up by supernova shock waves and compressed into dense molecular clouds, where star formation can occur relatively quickly. The recycling timescale for stellar wind material ranges from millions to billions of years, ensuring that the products of stellar nucleosynthesis eventually participate in multiple generations of cosmic chemical evolution. Half of all stars in the galaxy exist not as solitary suns, but as members of binary or multiple star systems, locked in gravitational embraces that can persist for billions of years or culminate in spectacular stellar catastrophes. These cosmic partnerships form during the star formation process, when fragmentation of collapsing molecular clouds creates multiple stellar embryos within the same gravitational potential well. The resulting orbital dance follows the same fundamental physics that governs planetary motion, yet stellar binaries operate on scales and timescales that dwarf anything found in planetary systems. The orbital periods of binary stars span an extraordinary range, from contact binaries that complete orbits in mere hours to wide pairs separated by thousands of astronomical units with orbital periods exceeding millions of years. Close binaries orbit so rapidly that their stellar surfaces nearly touch, creating elongated, egg-shaped stars that exchange material through gravitational tidal forces. Wide binaries appear as separate stars even through powerful telescopes, their gravitational connection revealed only through decades of careful astrometric measurements that detect their subtle orbital motion against the background of more distant stars. The physics governing binary star evolution depends critically on the ratio between orbital separation and stellar radius. When stars remain well separated throughout their lives, they evolve essentially as single stars, with gravitational interactions producing only minor perturbations to their structure and nuclear burning rates. But when one component expands during red giant evolution to fill its Roche lobe, the gravitational boundary within which material remains bound to that particular star mass transfer begins and fundamentally alters the evolutionary path of both stellar components. Mass transfer in binary systems creates some of the astronomy's most exotic phenomena, as material flows from the evolved primary star onto its compact companion. The transferred matter carries angular momentum, forming an accretion disk around the mass-gaining star as conservation laws prevent the material from falling directly onto the stellar surface. Friction within these accretion disks heats the gas to temperatures exceeding millions of degrees, causing it to emit X-rays and ultraviolet radiation that can outshine the luminosity of both stellar components combined. The rate of mass transfer depends on the complex interplay between stellar evolution, orbital dynamics, and the gravitational potential of both stars. Conservative mass transfer, where material lost by one star is completely captured by its companion, can proceed stably for millions of years if the mass ratio and orbital separation remain within certain bounds. Non-conservative mass transfer, where significant amounts of material escape the binary system entirely, can cause rapid orbital evolution as the decreasing system mass allows the orbit to expand according to conservation of angular momentum. Algol-type eclipsing binaries represent a particularly well-studied class of mass-transferring systems where the orbital plane lies nearly edge-on to Earth. These systems show periodic brightness variations as the stars alternately eclipse each other, providing precise measurements of stellar masses, radii, and orbital parameters. The prototype system Algol itself demonstrates the Algol paradox. The more evolved star appears less massive than its companion, indicating that it has transferred significant mass during its evolution beyond the main sequence. Cataclysmic variables showcase the extreme end of binary evolution when a white dwarf accretes material from a red dwarf companion. The hydrogen-rich material accumulates on the white dwarf surface until density and temperature become sufficient to trigger explosive nuclear burning. These nova explosions blast the accumulated material back into space at velocities reaching thousands of kilometers per second, yet leave the underlying white dwarf essentially unchanged and ready to begin accreting material for the next explosive cycle. The timescales between nova outbursts depend on the mass transfer rate and the mass of the white dwarf, ranging from decades for rapidly accreting systems to thousands of years for slower mass transfer rates. Recurrent novae like T Coronii Borealis explode every few decades. While classical novae may require centuries or millennia between outbursts, these explosive events temporarily increase the system luminosity by factors of thousands to millions, making previously invisible stars briefly visible to the naked eye. Type Ia supernovae represent the ultimate fate of some mass-transferring binary systems when white dwarfs accrete enough material to approach the Chandrasekhar limit. The physics of these explosions remains debated, with competing models involving either single degenerate scenarios where one white dwarf accretes from a normal stellar companion, or double degenerate scenarios where two white dwarfs merge catastrophically. Both pathways can potentially trigger carbon detonation that completely destroys the white dwarf and releases energy equivalent to 5 billion times the Sun's annual luminosity output. The standardizable luminosity of Type Ia supernovae makes them crucial distance indicators for cosmological studies. Because these explosions occur when white dwarfs reach a specific mass threshold, they produce remarkably uniform peak luminosities that can be calibrated to measure distances to galaxies hundreds of millions of light-years away. Observations of distant Type Ia supernovae provided the first evidence for the accelerating expansion of the universe, leading to the discovery of dark energy and fundamentally changing our understanding of cosmic evolution. X-ray binaries form when compact objects like neutron stars or black holes accrete material from stellar companions, creating some of the most luminous X-ray sources in the galaxy. The gravitational potential energy released as material falls onto these compact objects converts efficiently to high-energy radiation, with black hole X-ray binaries achieving luminosities approaching 10⁻39 watts, roughly equivalent to the energy output of an entire galaxy. The X-ray emission varies on timescales from milliseconds to years, reflecting the complex dynamics of accretion flows in extreme gravitational fields. Millisecond pulsars represent recycled neutron stars that have been spun up through accretion from binary companions. The transferred material carries angular momentum that gradually increases the neutron star's rotation rate from the typical few-second periods of young pulsars to rotation periods measured in milliseconds. This spin-up process requires the accretion of roughly 0.1 solar masses, taking millions of years to transform a slowly rotating neutron star into a millisecond pulsar spinning hundreds of times per second. The orbital evolution of binary systems proceeds through several distinct phases as stellar evolution and mass transfer modify the system properties. Initially, circular orbits can become eccentric through tidal interactions and asymmetric mass loss. Orbital periods can increase or decrease depending on whether mass loss carries away more or less angular momentum than expected from simple conservation laws. Some systems undergo common envelope evolution, where the expanded envelope of a red giant star engulfs its companion, leading to rapid orbital decay as friction dissipates orbital energy. Only took 4 billion years for the Sun to remain single, but roughly half of all stellar systems formed as binaries or higher-order multiples during the same epoch. This binary fraction appears universal across different stellar masses and galactic environments, suggesting that binary formation represents a fundamental outcome of the star formation process rather than a rare occurrence. The prevalence of binary stars means that stellar evolution must be understood in the context of gravitational interactions that can dramatically modify the evolutionary paths followed by single stars. Gravitational wave astronomy has revolutionized the study of compact binary systems by providing direct detections of merging neutron stars and black holes. These observations reveal a population of compact binaries that survived the supernova explosions of both stellar components while maintaining sufficiently close orbits to merge within the current age of the universe. The gravitational wave signals carry precise information about the masses and spins of the merging objects, testing theories of stellar evolution and supernova physics under extreme conditions. The study of binary stars provides crucial insights into stellar masses, stellar evolution, and the physics of accretion processes under a wide range of conditions. Eclipsing binaries remain the primary method for determining accurate stellar masses and radii, while mass-transferring systems reveal how stars respond to changing boundary conditions during their evolution. The diversity of binary star phenomena demonstrates that stellar evolution in isolation represents only part of the story. The majority of stars must be understood as members of gravitationally bound systems, whose evolution depends on the complex interplay between nuclear physics, fluid dynamics, and orbital mechanics operating across cosmic timescales. When the most massive stars reach the end of their nuclear burning phases, they unleash explosions so violent that they briefly outshine entire galaxies containing hundreds of billions of stars. These supernovae represent the universe's most efficient factories for creating and distributing elements heavier than iron, forging gold, platinum, uranium, and dozens of other heavy elements in the extreme conditions that exist only during stellar death. The explosion itself unfolds in mere seconds, yet its consequences ripple through space and time for millions of years, enriching vast regions of the galaxy with the chemical elements essential for rocky planets and biological complexity. The pathway to core collapse supernovae begins when massive stars exhaust their capacity for nuclear fusion in their cores. Unlike lower mass stars that can avoid catastrophic collapse through mass loss or electron degeneracy pressure, stars more massive than 8 solar masses face an inevitable gravitational reckoning. Silicon burning in their cores produces iron-56, the most stable atomic nucleus, which cannot release energy through further fusion. As the iron core grows beyond the Chandrasekhar limit of 1.4 solar masses, no force in the universe can prevent gravitational collapse. The core collapse proceeds with shocking rapidity, compressing a region the size of Earth to a sphere merely 20 kilometers across in less than 1 second. The core density increases from roughly that of water to nuclear density 10^15 grams per cubic centimeter in the time required for light to travel from Earth to the Moon. This catastrophic implosion releases gravitational binding energy equivalent to 1044 joules, roughly 100 times more energy than the Sun will produce during its entire 10 billion year main sequence lifetime. Most of this enormous energy emerges as neutrinos, ghostly particles that interact so weakly with matter that they stream directly from the collapsing core without heating the overlying stellar material. Yet even the tiny fraction of energy that couples to matter roughly 1% of the total suffices to blow apart the entire star in an explosion that accelerates several solar masses of material to velocities exceeding 10,000 kilometers per second. The shock wave that accomplishes this feat begins when the collapse rebounds off the newly formed neutron star core, creating a pressure wave that propagates outward through the stellar envelope. The physics of supernova explosions involves some of the most complex interactions between nuclear physics, neutrino transport, magnetohydrodynamics, and general relativity found anywhere in the universe. Computer simulations of core collapse supernovae require massive supercomputers running for weeks to model the first few seconds after core bounce, tracking the propagation of neutrinos through dense matter while following the hydrodynamics of shockwave propagation through the stellar envelope. Despite decades of effort, the precise mechanism that transforms core collapse into successful explosion remains incompletely understood. The explosive nucleosynthesis that occurs during supernovae creates conditions unlike anywhere else in the contemporary universe. Temperatures exceed 1010 degrees Celsius, while neutron densities reach values comparable to those found in atomic nuclei. Under these extreme conditions, rapid neutron capture processes, the R process, can add dozens of neutrons to atomic nuclei faster than radioactive decay can remove them. This creates neutron-rich isotopes that subsequently decay through chains of beta decay reactions, building elements like gold, platinum, and uranium that cannot form through any other known astrophysical process. The R process operates on timescales of seconds to minutes, building from iron peak elements to the heavier stable isotopes through neutron capture rates that exceed 10 neutrons per nucleus per second. The extremely high neutron densities required for our process nucleosynthesis, exceeding 10⁻²4 neutrons per cubic centimeter, exist only in the innermost regions of core collapse supernovae, and possibly in the ejecta from neutron star mergers. Each R process event synthesizes roughly 1 Earth mass of elements heavier than iron, distributing these rare materials throughout the surrounding interstellar medium. The energy released during supernovae accelerates the stellar debris to velocities that remain supersonic for thousands of years after the explosion. This expanding shell of hot gas creates supernova remnants, glowing nebulae that mark the sites of ancient stellar explosions. The Crab Nebula, formed by the supernova observed by Chinese astronomers in 1054 CE, still expands at 500 kilometers per second nearly 1,000 years after the original explosion. The shocked gas within supernova remnants glows across the electromagnetic spectrum, from radio waves to gamma rays, as the blast wave sweeps up and heats the surrounding interstellar medium. Supernova remnants serve as cosmic particle accelerators, using magnetic field amplification and shockwave acceleration to boost charged particles to cosmic ray energies exceeding 10,000 to 15 electron volts. These cosmic rays, primarily protons and heavier atomic nuclei moving at nearly light speed, carry energy densities comparable to starlight and magnetic fields throughout the galaxy. The cosmic ray flux observed at Earth consists largely of particles accelerated in supernova remnants over the past few million years, making supernova responsible not only for chemical enrichment, but also for maintaining the galaxy's population of high-energy particles. The shock waves from supernovae compress nearby molecular clouds, triggering the gravitational collapse that leads to new episodes of star formation. This feedback process creates a self-regulating cycle where massive stars form, evolve, explode, and trigger the formation of new stellar generations. The compression and heating from supernova shocks can either promote star formation by increasing gas density or inhibit it by dispersing molecular clouds, depending on the mass and energy of the shock wave and the properties of the target material. Type Ia supernovae, caused by the thermonuclear explosion of white dwarf stars in binary systems, follow different physics but achieve similar chemical enrichment effects. These explosions completely destroy the white dwarf through carbon detonation, converting roughly one solar mass of carbon and oxygen into iron peak elements like nickel-56, iron-56, and chromium-52. The radioactive decay of nickel-56 to cobalt-56 to iron-56 powers the optical light curves of type Ia supernovae, creating the standardizable luminosities that make these events crucial distance indicators for cosmological studies. The distribution of elements created in different types of supernovae reflects the nuclear physics operating under distinct explosive conditions. Core collapse supernovae produce oxygen, silicon, and sulfur through explosive silicon burning, while also synthesizing R-process elements in their innermost regions. Type Ia supernovae specialize in iron peak elements, contributing roughly half of the iron found in the contemporary universe. The relative rates of these explosion types determine the chemical evolution of galaxies over cosmic time. Supernova rates in spiral galaxies like the Milky Way average roughly one explosion per century, though the actual intervals between supernovae in any given region can vary from decades to millennia, depending on local star formation history. Each explosion enriches roughly 1,000 cubic light-years of interstellar space with heavy elements, gradually increasing the metallicity of galactic gas. This enrichment process required billions of years to reach the levels observed in the solar system, where elements heavier than hydrogen and helium comprise roughly 2% of the total mass. Only took 10 million years for the most massive stars to evolve from main sequence hydrogen burning to core collapse and explosion, but the heavy elements they create will persist for the entire future history of the universe. The gold in jewelry, the uranium in nuclear reactors, and the rare earth elements in electronic devices all formed during the brief moments of extreme conditions that exist only in exploding stars. These elements represent archaeological evidence of stellar death, preserved in planets and living organisms billions of years after the supernovae that created them. Modern surveys discover hundreds of supernovae annually in distant galaxies, revealing the ongoing chemical enrichment occurring throughout the universe. Each detection provides insights into stellar evolution, nuclear physics, and galactic chemical evolution operating under conditions that existed billions of years ago. The light from these explosions carries spectroscopic signatures of freshly synthesized elements, allowing astronomers to study nuclear synthesis in real time as it occurs in galaxies across cosmic history. The energy injected by supernovae into the interstellar medium drives galactic fountains, flows of hot gas that rise thousands of light-years above galactic disks, before cooling and falling back toward the galactic plane. These fountains transport heavy elements synthesized in stellar cores to the galactic halo, mixing processed material throughout the galaxy and establishing the metallicity gradients observed in galactic chemical abundance patterns. The cumulative energy from millions of supernovae over galactic history has fundamentally shaped the structure and chemical composition of galaxies. making stellar death as important as stellar birth for understanding cosmic evolution. In the cosmic hierarchy of stellar objects, brown dwarfs occupy a shadowy realm between the smallest stars and the largest planets. These failed stars possess sufficient mass to trigger gravitational collapse and heating during formation, yet lack the minimum mass required to sustain hydrogen fusion in their cores, with masses ranging from roughly 13 to 80 times that of Jupiter. Brown dwarfs exist in a state of perpetual twilight, glowing dimly from the heat of their formation, while slowly cooling over billions of years until they fade into invisibility against the cosmic background. The formation process for brown dwarfs mirrors that of normal stars during the initial phases, beginning with the gravitational collapse of dense regions within molecular clouds. As the proto-brown dwarf contracts, gravitational potential energy converts to thermal energy, heating the central regions to millions of degrees. However, the core temperature never reaches the 10 million degrees Celsius required to initiate sustained hydrogen fusion through the proton-proton chain reaction. Instead, these objects burn briefly through deuterium fusion during their youth, consuming their limited supply of heavy hydrogen within the first few million years of existence. The physics governing brown dwarf structure depends critically on electron degeneracy pressure, the same quantum mechanical phenomenon that supports white dwarf stars. As brown dwarfs cool and contract, their central densities increase until electrons become degenerate, providing precious support that prevents further gravitational collapse. This creates objects with radii comparable to Jupiter, despite masses 10 to 80 times larger, yielding average densities between 1 and 100 grams per cubic centimeter, intermediate between those of gas giant planets and main sequence stars. The atmospheric composition and temperature structure of brown dwarfs create unique observational signatures that distinguish them from both stars and planets. The coolest brown dwarfs maintain surface temperatures below 500 degrees Celsius, allowing complex molecular chemistry to occur in their atmospheres. Water vapor, methane, and ammonia condense into clouds that drift through brown dwarf atmospheres, while exotic molecules like chromium hydride and iron hydride form under the low temperature, high-pressure conditions found nowhere else in the universe. Spectroscopic observations reveal that brown dwarf atmospheres undergo dramatic chemical transitions as they cool over time. Young brown dwarfs with temperatures exceeding 2000 degrees Celsius show spectra, dominated by metal oxides like titanium oxide and vanadium oxide, similar to the coolest M-type red dwarf stars. As they cool below 1500 degrees, these oxides disappear and are replaced by molecular features from water vapor and carbon monoxide, defining the L spectral class specifically created to describe brown dwarf properties. The coolest brown dwarfs, classified as T-dwarfs, show prominent methane absorption bands that create deep valleys in their infrared spectra. Methane forms only when temperatures drop below approximately 1000 degrees Celsius, and carbon monoxide becomes thermodynamically unstable relative to methane and water vapor. This chemical transition marks a fundamental change in atmospheric composition that has no analogue among main sequence stars, highlighting the unique physical conditions achieved in these ultracool objects. Cloud formation in brown dwarf atmospheres operates through condensation processes similar to weather systems on terrestrial planets, but involving exotic materials like silicate minerals and metallic iron. Silicate clouds form at temperatures around 500 degrees Celsius, creating particles composed of materials like forsterite and enstatite that would exist as rock on planetary surfaces. Iron clouds condense at slightly lower temperatures, forming droplets of liquid metal that rain through the brown dwarf atmosphere until they reach depths where high temperatures vaporize them back into gas. The rotation rates of brown dwarfs vary dramatically, with periods ranging from a few hours to several days. Rapid rotation creates significant ablateness, flattening these objects at their poles and creating equatorial bulges. The combination of rapid rotation and convective atmospheric dynamics generates complex weather patterns that create time-variable brightness as different atmospheric features rotate into view. Some brown dwarfs show brightness variations exceeding 10% as patchy cloud coverage modulates their thermal emission. Magnetic fields on brown dwarfs can achieve strengths comparable to those found on main sequence stars, despite the absence of nuclear fusion to power magnetic dynamo activity. Convection in brown dwarf interiors, driven by slow cooling and thermal energy transport, generates magnetic fields through the same dynamo processes that operate in stellar cores. These fields manifest through radio emission and occasional flare activity, revealing magnetic reconnection events similar to solar flares but occurring in objects too cool to sustain nuclear burning. The discovery of brown dwarfs required the development of infrared astronomy. Since these objects emit most of their energy at wavelengths longer than visible light, the first confirmed brown dwarf, Gliese 299b, was discovered in 1995 through infrared spectroscopy that revealed methane absorption features impossible to explain through any stellar model. This discovery validated theoretical predictions made decades earlier and opened an entirely new field of study focused on substellar objects. Binary brown dwarfs provide crucial laboratories for determining brown dwarf masses and testing theoretical models of their structure and evolution. Gravitational interactions in binary systems allow astronomers to measure dynamical masses with precision approaching 1%. Confirming that these objects indeed occupy the predicted mass range between planets and hydrogen-burning stars, some brown dwarf binaries have orbital periods measured in hours, indicating separations comparable to the radius of the Sun and creating systems where tidal forces significantly distort the shapes of both components. The cooling evolution of brown dwarfs follows predictable patterns that allow astronomers to estimate their ages and initial masses. Young brown dwarfs shine brightly in infrared wavelengths, powered by the thermal energy stored during their formation. As they radiate this energy into space, their surface temperatures and luminosities decline steadily over time. A brown dwarf formed 10 billion years ago now glows at temperatures below 300 degrees Celsius, cooler than Venus, and approaching the temperature of boiling water. Planetary systems around brown dwarfs challenge conventional understanding of planet formation processes. The low masses and weak gravitational fields of brown dwarfs should make planet formation difficult, according to standard models. Yet observations have revealed several planetary companions orbiting these failed stars. The planets appear to form through gravitational instability in circumstellar disks rather than through core accretion, suggesting that multiple pathways exist for planetary system formation. The population statistics of brown dwarfs reveal important constraints on the star formation process and the initial mass function. Brown dwarfs appear roughly 10 times less common than main sequence stars, yet they may represent the most numerous stellar mass objects in the galaxy when their long lifetimes are considered. Unlike main sequence stars, which eventually exhaust their nuclear fuel and evolve into white dwarfs, neutron stars, or black holes, brown dwarfs simply cool and fade without undergoing dramatic evolutionary transitions. Only took 20 years from theoretical prediction to observational discovery of brown dwarfs. Yet their study continues to reveal unexpected complexity in these seemingly simple objects. Their atmospheres display chemical diversity exceeding that found among main sequence stars, while their magnetic activity challenges theoretical understanding of dynamo processes in convective objects. The coolest brown dwarfs blur the distinction between stars and planets, creating objects with properties intermediate between stellar and planetary characteristics. The study of brown dwarfs provides insights into the minimum conditions required for nuclear fusion and the physics of matter under intermediate density and temperature conditions. They serve as laboratories for testing theoretical models of stellar structure, atmospheric dynamics, and magnetic field generation under conditions that bridge the gap between stellar and planetary physics. These failed stars represent a significant population of galactic objects that remained completely unknown until the final decade of the 20th century, demonstrating that major discoveries about the universe's contents remain possible even in the era of advanced astronomical surveys. As brown dwarfs continue cooling over cosmic time, they will eventually become invisible even to the most sensitive infrared telescopes. In the far future, when all nuclear burning has ceased and the universe has cooled to near absolute zero, brown dwarfs will join white dwarfs and stellar remnants as dark objects drifting through an increasingly empty cosmos. Their long cooling timescales exceeding trillions of years ensure that brown dwarfs formed today will persist as faint infrared sources long after the Sun has exhausted its nuclear fuel and the Milky Way has merged with the Andromeda Galaxy. Among the stellar populations that populate our galaxy, certain stars pulse with the mechanical precision of cosmic metronomes, expanding and contracting their outer layers in cycles that can be predicted with extraordinary accuracy. These variable stars, known as Cepheids, undergo periodic changes in brightness that follow mathematical relationships so reliable that astronomers use them as standard candles for measuring distances across millions of light-years of space. The pulsation mechanism that drives these stellar oscillations operates through a delicate interplay between nuclear energy generation, radiative transport, and the opacity changes that occur in partially ionized helium zones deep within stellar atmospheres. The physics underlying Cepheid variability begins in a narrow zone within the stellar envelope where helium atoms exist in a partially ionized state. As the star contracts during its pulsation cycle, this helium zone becomes denser and hotter, causing additional helium atoms to lose their second electron through thermal ionization. The newly ionized helium atoms absorb radiation more efficiently than neutral helium, increasing the opacity of this stellar layer and trapping energy that would otherwise escape to space. This energy buildup heats and expands the helium zone, driving the stellar envelope outward until reduced density and temperature allow helium to recombine and become transparent again. The resulting pulsation cycle creates periodic changes in stellar radius, surface temperature, and luminosity that follow predictable patterns established by the stellar mass, luminosity, and internal structure. The classical Cepheids, with periods ranging from 1 to 100 days, vary in brightness by factors of 2 to 10 as their surface areas and temperatures oscillate in phase with their radial pulsations. The period luminosity relationship discovered by Henrietta Swan Leavitt in 1912 revealed that intrinsically brighter Cepheids pulsate with longer periods, providing a cosmic ruler for measuring astronomical distances. The mathematical elegance of Cepheid pulsations emerges from their adherence to fundamental stellar structure equations. The pulsation period depends primarily on the stellar density. According to the relationship discovered by Arthur Eddington, the period in days equals approximately 1/10 the square root of the stellar density in solar units. This relationship explains why more luminous Cepheids, which have lower average densities due to their larger radii, pulsate with longer periods than their less luminous counterparts. Different types of Cepheid variables reveal the complexity of stellar pulsation physics and stellar evolution pathways. Classical Cepheids are massive, young stars undergoing helium burning in their cores, typically with masses between 4 and 20 times that of the Sun. These population Cepheids formed from metal-rich gas in the galactic disk and retain the chemical signatures of previous generations of stellar nucleosynthesis. Type II Cepheids, also called W Virginis stars, are older, lower-mass stars with subsolar metallicities that represent an earlier epoch of galactic chemical evolution. The discovery of Cepheid variables in external galaxies revolutionized understanding of cosmic distances and the scale of the universe. Edwin Hubble's observations of Cepheids in the Andromeda Galaxy conclusively demonstrated that spiral nebulae are independent stellar systems comparable to our own Milky Way, rather than nearby gas clouds within our galaxy. This measurement established the extragalactic distance scale and provided the foundation for discovering the expansion of the universe through observations of more distant galaxies. RR Lyrae stars represent another class of pulsating variables that serve as distance indicators, particularly for globular clusters and the galactic halo. These horizontal branch stars burn helium in their cores while undergoing hydrogen shell burning, creating internal structure that drives pulsations with periods ranging from half a day to 1 day. R Lyrae variables all have roughly the same intrinsic luminosity regardless of their pulsation period, making them excellent standard candles for measuring distances within the local group of galaxies. The pulsation mechanism in R Lyrae stars operates through the same helium ionization zone physics that drives Cepheid variability. But the lower masses and different evolutionary states of R Lyrae stars create distinct pulsation properties. Bailey types RAB and RRC show different light curve shapes and period distributions, reflecting different pulsation modes excited by the same driving mechanism, operating under slightly different physical conditions. The study of R Lyrae pulsations provides insights into horizontal branch stellar structure and the late stages of low-mass stellar evolution. Long-period variables like Mira stars undergo much more dramatic brightness changes, often varying by factors of hundreds as they pulsate with periods lasting months to years. These evolved red giants have extended in tenuous atmospheres where pulsation-driven shock waves can trigger complex chemical processes and dust formation. The pulsation mechanism involves multiple driving zones throughout the extended stellar envelope, creating irregular light curves that reflect the chaotic dynamics of shock wave propagation through stratified stellar atmospheres. The study of stellar pulsations through astroseismology provides unprecedented insights into stellar interiors that cannot be observed through any other technique. Just as geologists study Earth's interior structure through earthquake waves, astronomers can probe stellar cores by analyzing the frequencies and amplitudes of stellar oscillations. Different pulsation modes penetrate to different depths within stars, carrying information about temperature, density, and composition variations throughout stellar interiors. Solar-like oscillations have been detected in thousands of stars through space-based photometry missions like Kepler and TESS, revealing acoustic waves driven by convection in stellar envelopes. These pressure modes, or P modes, provide measurements of stellar masses, radii and ages with precisions approaching those achieved for the Sun through helioseismology. The technique has revolutionized stellar astrophysics by allowing direct determination of fundamental stellar properties for large samples of stars across the galaxy. White dwarf pulsators create another class of variable stars where stellar oscillations probe the physics of degenerate matter under extreme conditions. DB white dwarfs pulsate through G-mode's gravity waves that propagate through compositionally stratified interiors, while DAV white dwarfs show P-mode pulsations driven by partial ionization in their thin hydrogen atmospheres. The periods and period spacings of white dwarf oscillations provide direct measurements of white dwarf masses, temperatures, and internal structure. The mathematical techniques developed for analyzing stellar pulsations have applications far beyond astronomy, contributing to fields like geophysics, acoustics, and plasma physics. The inverse problem of inferring internal structure from observed oscillation frequencies requires sophisticated mathematical methods that have found applications in medical imaging, materials science, and other areas where internal properties must be determined from external measurements. Modern surveys discover thousands of new variable stars annually, revealing the ubiquity of stellar pulsations across different masses, ages, and evolutionary states. The Gaia space mission has detected brightness variations in hundreds of millions of stars, creating the largest catalogue of variable stars ever assembled. This census reveals that stellar variability represents a common rather than exceptional phenomenon, with most stars showing some level of brightness variation when observed with sufficient precision over adequate time baselines. Only took 100 years from Leavitt's discovery of the period luminosity relationship to the detection of stellar oscillations in thousands of stars through space-based astroseismology. This progression from individual variable star discoveries to systematic surveys of stellar pulsations illustrates the evolution of observational astronomy, from cataloguing individual objects to statistical studies of entire stellar populations. The precision timing required for astroseismology, measuring brightness changes at the level of parts per million, pushes the limits of current technology, while providing unprecedented insights into stellar physics. The future of variable star astronomy lies in combining astroseismic measurements with other observational techniques to create comprehensive models of stellar structure and evolution, interferometric measurements of pulsating star diameters, spectroscopic studies of pulsation-driven atmospheric dynamics, and theoretical modelling of three-dimensional stellar pulsations will continue advancing our understanding of these cosmic chronometers. Variable stars serve as natural laboratories where the fundamental physics of stellar interiors can be tested under conditions impossible to reproduce in terrestrial experiments, making them invaluable tools for advancing both stellar astrophysics and fundamental physics. The galaxy preserves within its stellar populations the complete archaeological record of star formation and chemical evolution, extending back nearly to the cosmic dawn. Astronomers divide these stellar generations into broad categories based on their heavy element abundances and spatial distributions, creating a taxonomy that reveals how the Milky Way assembled itself through billions of years of mergers, star formation episodes, and the gradual enrichment of interstellar gas with elements forged in stellar cores. Population Y stars, which include our Sun and most visible stars in the night sky, represent the current generation of metal-rich stars formed from gas already enriched by countless previous stellar life cycles. Population 1 stars contain roughly 2% heavy elements by mass, a metallicity that astronomers express as approximately solar abundance. This chemical composition reflects the cumulative effect of 11 billion years of stellar nuclear synthesis, during which massive stars created oxygen, silicon, and iron through fusion processes, then distributed these elements throughout the galaxy via supernova explosions and stellar winds. The carbon, nitrogen, and fluorine found in population 1 stars originated primarily in the envelopes of evolved intermediate mass stars, while elements heavier than iron form through neutron capture processes in supernovae and neutron star mergers. The spatial distribution of population 1 stars traces the current structure of galactic star formation, concentrated in the thin disk where molecular clouds provide raw material for continued stellar birth. These stars orbit the galactic center in nearly circular paths that follow the disk's rotation curve, maintaining small vertical excursions above and below the galactic plane. Their kinematics reflect formation from gas that had already settled into ordered rotation, contrasting sharply with the more random motions exhibited by older stellar populations formed during earlier, more chaotic epochs of galactic evolution. Population 2 stars represent an earlier generation formed when the galaxy contained far fewer heavy elements, typically showing metallicities reduced by factors of 10 to 1000 compared to solar values. These metal-poor stars populate the galactic halo and thick disk, following highly eccentric orbits that carry them far from the galactic plane. Their chemical compositions preserve signatures from an era when the galaxy had experienced only limited stellar processing, providing direct observational access to conditions that existed billions of years ago when the Milky Way was still assembling from smaller constituent galaxies. The most extreme population 2 stars, with metallicities below 1% of solar values, likely formed from gas enriched by only the first few generations of massive stars. These ancient objects show distinctive abundance patterns that reflect the unique nucleosynthesis occurring in very massive, metal-free stars that exploded as pair instability supernovae. The detection of such stars provides observational constraints on theories of early star formation and the initial mass function of the first stellar generation to form after the cosmic dark ages. Globular clusters serve as fossil remnants of intense star formation episodes that occurred during the galaxy's youth, preserving coeval populations of ancient stars that formed simultaneously from the same gas cloud. The majority of globular clusters contain population 2 stars with ages approaching 13 billion years, making them among the oldest objects in the universe. Their stellar populations show evidence for multiple episodes of star formation within individual clusters, revealing complex early histories that challenge simple models of globular cluster formation and evolution. The horizontal branch morphology within globular clusters provides a sensitive diagnostic of stellar population properties, particularly the age and helium abundance of cluster stars. Blue horizontal branch stars burn helium in their cores while maintaining hot, compact envelopes, while red horizontal branch stars have evolved to cooler surface temperatures during the same evolutionary phase. The ratio of blue to red horizontal branch stars depends on subtle differences in stellar mass and composition that reflect the detailed conditions present during cluster formation. Chemical abundance patterns within stellar populations reveal the relative contributions of different nucleosynthesis sources to galactic chemical evolution. The alpha element enhancement observed in halo stars elevated abundances of oxygen, magnesium, silicon, and calcium relative to iron indicates rapid chemical enrichment by core collapse supernovae before type Ia supernovae had time to contribute significant amounts of iron peak elements. This abundance pattern provides evidence for short, intense episodes of star formation during the galaxy's early assembly phase. The discovery of stellar streams in the galactic halo provides direct evidence for ongoing galactic cannibalism, where the Milky Way continues to accrete smaller satellite galaxies and disrupts them through tidal forces. These streams contain stars with distinct chemical signatures that reveal their extragalactic origins, allowing astronomers to reconstruct the accretion history that built the galactic halo. The Sagittarius stream, formed by the ongoing disruption of the Sagittarius dwarf galaxy, wraps completely around the sky and contains stars with abundance patterns distinct from native halo populations. Ultra-faint dwarf galaxies represent the most metal-poor stellar systems known, containing stars with heavy element abundances approaching the theoretical minimum required for star formation. These satellite galaxies preserve chemical signatures from the epoch of reionization, when the first stars and quasars began heating and ionizing the intergalactic medium. Their stellar populations provide insights into star formation under primordial conditions and the minimum halo masses required to retain gas and form stars in the early universe. The neutron capture element abundances in different stellar populations trace the relative importance of S-process and R-process nucleosynthesis throughout galactic history. Halo stars show predominantly R-process signatures, indicating that neutron star mergers or rare core collapse supernovae dominated heavy element production during early galactic evolution. Disk stars display increasing S-process contributions from asymptotic giant branch stars, reflecting the longer timescales required for intermediate mass stars to evolve and contribute to chemical enrichment. Lithium abundances in population 2 stars create the lithium problem, a significant discrepancy between observed lithium levels and those predicted by Big Bang nucleosynthesis models. The most metal-poor stars show lithium abundances roughly 3 times lower than theoretical expectations, suggesting either that lithium has been depleted through stellar processes or that our understanding of primordial nucleosynthesis requires modification. This puzzle highlights how stellar archaeology can probe not only stellar evolution, but also fundamental cosmology and nuclear physics. White dwarf cooling ages provide independent constraints on the age of the galactic disk by measuring the coolest white dwarfs in the solar neighborhood. These stellar remnants have been cooling since their formation, and their surface temperatures provide lower limits on the age of the disk's stellar population. White dwarf cooling ages of 8 to 10 billion years for the oldest disk white dwarfs suggest that the thin disk began forming roughly 2-4 billion years after the Big Bang, consistent with estimates from stellar evolution models applied to main sequence turn-off stars. The metallicity gradient observed across the galactic disk reveals the inside-out formation history of the Milky Way, where the inner regions formed stars earlier and achieved higher metallicities than the outer disk. This gradient reflects the efficiency of gas inflow, star formation, and metal mixing as functions of galactocentric radius. The flattening of the metallicity gradient at large radii may indicate disruption by spiral density waves, or the accretion of low metallicity gas from the intergalactic medium. Only took 8 billion years for stellar nucleosynthesis to increase the galaxy's heavy element content from essentially zero to the levels observed in the solar system. But this enrichment proceeded at different rates in different galactic components. The halo reached its current metallicity within the first billion years through rapid star formation and chemical enrichment, while the thick disk continued evolving for several billion years, and the thin disk has maintained ongoing star formation and chemical evolution up to the present epoch. Modern spectroscopic surveys like APOG, GALA, and GAIS-YA ESC have measured chemical abundances for hundreds of thousands of stars across multiple galactic components, creating detailed maps of chemical evolution throughout the galaxy. These surveys reveal the complexity of galactic chemical evolution, showing that simple models of homogeneous chemical enrichment cannot explain the observed abundance patterns. Instead, the galaxy appears to have assembled through multiple episodes of gas accretion, star formation, and mixing that created the diverse stellar populations observed today. The study of stellar populations provides crucial insights into galaxy formation and evolution on cosmic scales, revealing how the interplay between dark matter dynamics, gas physics, and stellar feedback shapes the properties of galaxies like our own. The chemical and kinematic signatures preserved in stellar populations serve as fossil records of physical processes operating during epochs when the universe was much younger and galaxies were still assembling their current structure. Each stellar generation carries within its chemical composition the history of all previous generations, creating an archaeological record that extends back toward the cosmic dawn. Each star in the night sky serves as a portal through time, its light carrying messages encoded in wavelengths that reveal the physical conditions, chemical composition, and nuclear processes operating within stellar cores across vast reaches of cosmic history. When astronomers analyze starlight through spectroscopes, they decode information that has traveled for years, centuries, or millennia to reach Earth, creating a form of temporal archaeology that allows us to study stellar physics as it existed in the past. The photons streaming from distant stars began their journeys when human civilizations were taking their first tentative steps toward understanding the cosmos, finally arriving to meet our instruments in a convergence of ancient light and modern technology. The concept of stars as portals emerges from the fundamental physics of electromagnetic radiation and the finite speed of light. Every photon carries within its energy and wavelength a precise record of the conditions present when it was emitted from a stellar surface. The continuous spectrum reveals the star's surface temperature through blackbody radiation laws, while absorption lines encode the chemical composition and physical state of stellar atmospheres. Doppler shifts indicate stellar motion through space. Magnetic field splitting reveals the strength of stellar magnetic fields, and subtle periodic variations can disclose the presence of orbiting planets or stellar companions. The temporal dimension of stellar observation creates a unique form of time travel, where more distant stars appear as they existed further in the past. The nearest star beyond our Sun, Proxima Centauri, shows us conditions that existed 4.2 years ago, while stars visible to the naked eye typically display their states from decades or centuries in the past. The most distant individual stars observable through modern telescopes reveal stellar physics operating billions of years ago, when the universe was much younger and galaxies were still forming their first stellar generations. This light travel time effect transforms stellar astronomy into a study of cosmic evolution, where observations at different distances sample stellar populations from different epochs. Nearby stars represent the current generation of stellar formation and evolution, enriched by billions of years of previous stellar processing. Intermediate distant stars show the galaxy as it existed during various stages of its chemical evolution, while the most distant observable stars preserve conditions from the early universe, when heavy element abundances were much lower than today. The information content carried by starlight depends on the sophistication of observational techniques and the theoretical frameworks available for interpretation. Early astronomers could determine only basic properties like brightness and color, but modern spectroscopy reveals stellar masses, radii, ages, chemical compositions, rotation rates, magnetic field strengths, and evolutionary states. Space-based observations extend this information to wavelengths blocked by Earth's atmosphere, while interferometry provides spatial resolution sufficient to image stellar surfaces and circumstellar environments. Stellar spectroscopy operates as a form of remote nuclear physics, allowing astronomers to study fusion processes occurring under conditions impossible to reproduce in terrestrial laboratories. The ratios of different isotopes in stellar atmospheres reveal the efficiency of various nuclear burning phases, while the presence of technetium, an element with no stable isotopes in stellar spectra, provides direct evidence for ongoing neutron capture nucleosynthesis. These observations test theoretical models of stellar structure and nuclear physics under extreme conditions of temperature, density, and magnetic field strength. The chemical signatures preserved in stellar atmospheres create a fossil record of galactic chemical evolution, showing how successive generations of stars have gradually enriched the interstellar medium with heavy elements. The abundance patterns observed in different stellar populations constrain theories of stellar nucleosynthesis, supernova explosion mechanisms, and the timescales of various enrichment processes. Stars with unusual abundance patterns reveal rare nucleosynthesis events or the effects of mass transfer in binary systems, expanding our understanding of the diverse pathways through which elements form and distribute throughout the galaxy. Variable stars serve as particularly information-rich portals, broadcasting continuous streams of data about stellar interior physics through their periodic brightness and spectral changes. Pulsating variables reveal stellar masses and evolutionary states through their pulsation periods and amplitudes, while eclipsing binaries provide direct measurements of stellar parameters through the geometry of their orbital systems. Novae and supernovae transmit information about explosive nucleosynthesis and the final stages of stellar evolution, often outshining their host galaxies and making their signals detectable across billions of light-years. The detection of exoplanets through stellar observations transforms stars into portals for studying planetary system formation and evolution. Transit photometry reveals planetary sizes and orbital periods, while radial velocity measurements determine planetary masses and orbital eccentricities. Atmospheric characterization through transmission spectroscopy allows astronomers to study exoplanet atmospheric composition and structure, using the star as a backlight to probe the chemical properties of distant worlds. These techniques extend our ability to study planetary physics far beyond the confines of our own solar system. Stellar astronomy increasingly relies on statistical studies of large stellar samples to understand galactic structure and evolution. Surveys like Gaia, which has measured parallaxes and proper motions for over 1 billion stars, create three-dimensional maps of stellar positions and velocities that reveal the galaxy's gravitational structure and dynamical history. These kinematic studies trace stellar streams from disrupted satellite galaxies, identify coeval stellar groups with common origin, and measure the galaxy's rotation curve and dark matter distribution. The future of stellar astronomy as temporal archaeology depends on advancing observational capabilities and theoretical understanding. Next-generation telescopes will detect and characterize stars in the most distant observable galaxies, pushing stellar studies back to within 1 billion years of the Big Bang. These observations will probe stellar physics during the epoch when the first heavy elements were being synthesized, and will test theories of stellar formation under primordial conditions with minimal heavy element content. Gravitational wave astronomy adds a new dimension to stellar studies by detecting the final moments of stellar evolution when compact objects merge or collapse. These observations provide direct measurements of neutron star and black hole masses, spins, and merger rates that complement electromagnetic observations of stellar populations. The combination of gravitational wave and electromagnetic signals from events like neutron star mergers creates multi-messenger astronomy that reveals stellar death processes with unprecedented detail. The interpretation of stellar signals as messages from the past requires careful consideration of systematic effects and observational biases that can distort our view of stellar populations. Interstellar extinction preferentially obscures blue light, making distant stars appear redder and cooler than their true properties. Stellar evolution affects the observable properties of stellar populations over time, creating selection effects where only certain types of stars remain detectable after billions of years of evolution. Only took 400 years from Galileo's first telescopic observations to the current era of precision stellar astronomy. Yet each improvement in observational capability has revealed new layers of complexity in stellar physics and galactic evolution. The progression from visual observations to photographic astronomy to digital detectors has increased the precision of stellar measurements by many orders of magnitude, while extending observations to wavelengths across the electromagnetic spectrum. Each photon of starlight represents a quantum messenger that has travelled across space and time to deliver information about the nuclear physics, chemical evolution, and gravitational dynamics operating in distant stellar environments. These electromagnetic signals carry the complete history of stellar birth, evolution, and death encoded in their wavelengths, intensities, and temporal variations. Stellar astronomy thus becomes a form of cosmic archaeology, where the analysis of ancient light reveals the physical processes that have shaped the universe throughout its 13.8 billion year history. The stars serve as portals not only through space but through time itself, connecting our present moment to the deep past when the physical conditions recorded in starlight first came into existence. Each stellar observation represents a form of communication across cosmic distances and timescales, where the language consists of electromagnetic radiation and the message contains the fundamental physics governing stellar structure, nuclear burning, and galactic chemical evolution. In studying starlight, we engage in a conversation with the cosmos itself, reading the stories written in wavelengths of light that began their journeys when the universe was young and are only now reaching our telescopes to share their ancient secrets. The photons reaching Earth tonight began their journeys in stellar cores when ice sheets covered vast continents and early humans were discovering fire. They struggled outward through stellar plasma for millennia, scattered by countless interactions with electrons and ions, gradually losing energy and shifting wavelengths as they thermalized in the dense stellar interiors. Each photon that finally escaped a stellar surface carried with it the signature of nuclear fusion hydrogen transformed to helium in the deepest furnaces of creation. Across the empty spaces between stars, these messengers travelled without impediment, maintaining perfect fidelity to their original wavelengths and intensities. Some photons journeyed for decades from nearby stellar neighbours, while others crossed centuries or millennia of space from more distant suns. A few arrived from such remote stellar populations that they began their voyages when the galaxy itself was younger, carrying information from epochs when heavy elements were scarce and stellar physics operated under different chemical conditions. Tonight, as telescopes and instruments capture this ancient light, each photon completes its cosmic mission by transferring its energy to electronic detectors that convert electromagnetic radiation into digital signals. The wavelength of each photon reveals the temperature of the stellar surface that emitted it. The intensity speaks of the star's luminosity and distance. Subtle absorption features encode the chemical composition of stellar atmospheres, while periodic variations whisper of planets, stellar companions, or internal pulsations. The stars themselves continue their patient work, fusing hydrogen into helium at rates determined by the precise balance between gravitational collapse and thermal pressure. Most will burn steadily for billions of years more, gradually accumulating helium ash in their cores until evolutionary changes force them toward red giant phases, white dwarf cooling, or more dramatic endpoints. The nuclear reactions proceeding now in stellar cores will produce photons that will not reach Earth for hundreds of thousands of years, carrying messages about stellar physics as it exists in our current epoch, in globular clusters scattered throughout the galactic halo. Ancient red giants slowly expel their outer envelopes while their cores contract toward white dwarf configurations. The planetary nebulae they create will glow for thousands of years, illuminated by ultraviolet radiation from the exposed stellar cores before fading into invisibility. New generations of brown dwarfs continue their inexorable cooling, their surface temperatures dropping by degrees each million years as they radiate away the thermal energy stored during their formation. Binary neutron stars spiral inward as gravitational wave radiation carries away their orbital energy. Approaching merger events that will synthesize gold and platinum in quantities sufficient to enrich entire stellar neighborhoods. Massive stars in their final phases build up iron cores that will soon collapse, triggering supernova explosions that will outshine their host galaxies and scatter heavy elements across thousands of light years of interstellar space. The galaxy rotates with stately precision, its spiral arms sweeping through space at orbital velocities approaching 200 kilometers per second. Molecular clouds drift in and out of spiral density waves, some triggered to collapse and form new stellar generations, while others remain quiescent for millions of years. The chemical composition of the interstellar medium slowly increases as stellar winds and supernova explosions add freshly synthesized elements to the cosmic reservoir from which future stars will form. Somewhere in distant galaxies, stellar populations follow similar evolutionary patterns under physical laws that remain constant across cosmic space and time. The nuclear physics that governs fusion rates, the quantum mechanics that determines atomic structure, and the gravitational dynamics that shape stellar evolution operate with identical precision, whether in our local stellar neighborhood or in galaxies so remote that their light has traveled for billions of years to reach our telescopes. The cosmic microwave background continues its expansion-driven cooling, its temperature now just 2.7 degrees above absolute zero. This primordial radiation, released when the universe first became transparent to light, provides a baseline against which all subsequent electromagnetic signals must be measured. Stellar radiation adds energy to this cosmic background, but the expansion of space dilutes this contribution until, in the far future, stellar sources will fade and the universe will return to darkness, illuminated only by the cooling glow of its primordial fire. Time flows forward with its characteristic asymmetry, converting stellar nuclear fuel into radiation and heat that dissipates into the growing volume of expanding space. Entropy increases as organized stellar structures gradually surrender their concentrated energy to the cosmic background, following thermodynamic laws that ensure eventual equilibrium. Yet this approach to maximum entropy proceeds so slowly that countless stellar generations will live and die before the universe reaches its final state of uniform temperature and darkness. In the deepest quiet of space, photons continue their eternal journeys, carrying the stories of stellar birth and death across distances measured in light years and time intervals spanning cosmic epochs. Each wavelength preserves information about the nuclear processes that created it, maintaining perfect fidelity to the physical conditions present at the moment of emission. The universe thus becomes a vast library of electromagnetic radiation, where every photon serves as a page recording the history of matter and energy under the influence of fundamental forces, The night sky overhead displays this cosmic correspondence in progress, each visible star contributing photons to a continuous stream of information flowing inward from all directions. Behind the familiar constellations, radio telescopes detect longer wavelengths from pulsars and synchrotron sources, while infrared detectors capture thermal emission from dust clouds warmed by stellar radiation. Across the electromagnetic spectrum, the cosmos broadcasts its ongoing story of gravitational collapse, nuclear fusion, chemical evolution, and the patient transformation of hydrogen into all the elements that populate the periodic table. As consciousness turns towards sleep, stellar processes continue their work with the same precision that has maintained them for billions of years. Nuclear reactions proceed at rates determined by quantum tunneling probabilities and stellar core conditions. Gravitational fields shape spacetime according to Einstein's equations. Electromagnetic radiation propagates at light speed according to Maxwell's laws. The fundamental constants that govern these processes remain unchanged, ensuring that stellar physics operates with consistency across cosmic space and time. Stars serve as portals through which we glimpse the universe's deep history and its probable future. In their light, we read the story of cosmic evolution from primordial hydrogen and helium to the complex chemistry that enables rocky planets and biological complexity. Through stellar observations, we trace the pathways that connect the Big Bang to the present moment, following the nuclear processes that built atoms, the gravitational dynamics that assembled galaxies, and the thermodynamic flows that drive cosmic evolution towards states of increasing entropy and ultimate equilibrium. The photons that warm our faces tomorrow will complete journeys that began in stellar cores when mammoths walked the Earth. They carry with them the patient message of nuclear fusion, encoded in wavelengths that speak of temperatures, densities, and chemical compositions existing in the deepest interiors of distant suns. In receiving this ancient light, we participate in a cosmic conversation that spans space and time, connecting our brief moment of awareness to the vast scales on which stellar evolution unfolds its story of creation, transformation, and the eternal journey of energy through an expanding universe.